So here we go. So we're talking about active solar energy applications. And in that sense, what we are going to use is to make use of the solar energy in basically two major modes, which are heating, either the mode of space heating, air heating, not only space heating, but it can be used, for example, for drying, and the other major utilization, which is related to the water heating. So the energy reaching to the surface of the earth from the sun over any period of time is always greater than the needs at that specific time. It should be, on the other hand, captured at a suitable temperature that would be needed for a later use, and that actually combines the issue of energy storage that brings come to the picture. Solar devices are basically the devices that are created or manufactured for that, so that they absorb the solar energy and utilize it either instantaneously or at a later time. Direct heating has always been over history the standard way of utilizing solar energy. It has been used for crop drying, for space heating, for water heating, for cooking, and for driving power cycles as well. So many power plants are based on solar energy, having either a tower or a parabolic trough, as we have seen with Dr. Mkhitar earlier. And some even have been used for power in terms, so far it's not yet widespread having solar cars, but there are races that are being done maybe twice a year in several places, which is concerned about this and encouraging the utilization of solar energy in operating engines or car, or however, I have to mention that this is a solar PV application, but it's utilization of solar energy anyway. The diffuse and temporary available solar energy requires large collection area to capture energy and convert it into heat. And this is one probably of the what can I say, resistors to the widespread of this technology to the level it should be, is that although the efficiency of a solar collector is on the high side, but still the prices of the solar collectors and the availability of surfaces where the solar collectors are going to be spread on is an added value to the capital cost, and that's what makes in some cases the payback period is not only a matter of a few months, but it can even reach for a few years. Storage is another issue which is adding to the cost. Why storage? Because we need to make use of the solar energy at times where it's either cloudy, or in other cases it could be at night time. So cloudy days in winter, night times is times where the solar energy is not there, yet we need to use it. So we have to use like good storage system which are well insulated so that we can make use of that energy anytime. Flat plate solar collectors is the most common among all of these. They are very much commonly used in the system. And the flat plate solar collectors are there with a major layout, but different designs, and lots of companies that are producing these solar collectors. Actually, you can find these solar collectors in many places in the world being manufactured. Examples are, you can find very good collectors in the US, in Germany, in Italy, and definitely in China. And locally, Al-Khazaf al-Saudi or Saudi Ceramics started to produce solar collectors as well, and you can find them there. Turkey is a part of the game where you can find so many solar collectors in the market here that are basically manufactured in Turkey. So they are used. Some of them are, the name looks conventional to us because we have been seeing the solar collectors in many places. However, a new technology came to the picture of the solar collectors, that they are making the solar collectors and they apply vacuum in them. Applying vacuum or using evacuated flat plate solar collectors is rather new technology, and this technology actually is pretty efficient. It can have water heated to very high temperatures, and that's another interesting sort of application for these collectors. What we see here is just layouts of different types of collectors. Some of them are covered with glass. Glass here is what we refer to as glazing. So the first one on the top has glazing. The glazing passes the water, the solar energy in, the solar radiation in. Solar radiation can penetrate through or can transmit through the glass because it is coming from a short wavelength source, which is the sun, high temperature, short wavelength. On the other hand, when the absorber plate inside and these pipes are receiving heat inside of them, the hot water inside these tubes cannot emit its solar radiation out because the glass has that greenhouse effect or phenomena that it is transparent to short wavelength radiation, which is coming from the sun, but it is opaque for long wavelength radiation. So it does not allow the radiation to go from inside to the outside. Whatever will penetrate through the glass has radiation surface properties, which are absorptivity. It can absorb part of the energy. The glass itself gets heated. The major property is transmissivity. It transmits the solar energy through. The third property is the reflectivity, so it can reflect back some of the solar energy. But glasses are selected in a way that they can transmit the maximum amount of energy through them. So transmissivity here can exceed 90%, which means that more than 90% falling on the glass is being transmitted down. And when it's transmitted down, there is a black surface here. We call it an absorber plate. The absorber plate is black. Why black? Because the black color absorbs all the incident radiation falling into it and converts it into heat. And the heat here is going to be transferred to the water inside the tubes. So the tubes are going to be heated accordingly. Or you might not have tubes in that case, but you have like partitions like that. And these partitions are basically airflow channels. So you are heating the air. Or there is no glass at all and you are heating water, but heating the water here is not coming to very high temperature. This is normally to a moderate temperature, and that's why the unglazed solar collectors are being used for applications like swimming pools. So we have a structure or a box that can hold and protect the components that are inside so that they can withstand the weather conditions and minimize the heat loss. You can see here this color. It means that we're talking about insulation of the system so that we are minimizing the heat losses as much as we can. The fins or the extended surfaces, that tubes could be fin tubes, the extended surfaces to the channels, because fins or extended surfaces, they increase the surface area. Increasing the surface area increases the heat transfer rate. These are some samples of flat plate collectors that are or that can be installed on top of houses. And this is one of the good things in terms of space, that you can make use of the space that you have and you can put it on the roof of your building, provided that the roof is at a suitable angle. If not, then anyway, it's still the best option to do. Is to have your system placed on the roof. And definitely you're going to select the roof that faces south, and this is where you are going to put your solar collector. The solar collectors are here, but the piping, the tank, and the storage are extended or connected by pipes to the basement of a building. Glass is the cover for the solar collector, and you'd be lucky to have, or you can invest in having a low iron content of the glass so that it can transmit great insulation fraction, especially in the infrared spectrum range, up to 3 micrometer. So the collector efficiency increases this way. Low iron glass is more expensive. However, you can use it based on economical analysis. You can just see when you put the low iron glass into, or you use a system with low iron glass, how much will be the investment? And accordingly, you can see whether it's worth or not. I mean, you are talking about higher efficiency, which means that you may use less units of the solar collectors. You are paying more for each unit, but you are using less units in general, so that it might counter balance the investment that you are putting. Solar collectors with liquid as the transport fluid. This is very common because most of the collectors that we are using, or the ones that you can see them spread here in the kingdom or many other places, especially for domestic use in our area, are basically for water heating. Air heating would be there for cold countries. This is where basically they might be interested in having direct heating for the air. However, they can still do water heating. I've seen it in different designs, doing the water heating and then passing a heat exchanger by the water to heat the air, and then air would be used for heating. So both would be there. Water heating is more common. Water has many advantages. This is why it's more common, because it has a higher specific heat. So you can easily transfer energy in water, hot water or even cold water, more than air. Air can be heated very easily. I have solar collectors at the beach. They are basically evacuated at our beach here, KFUM Beach, in our research area. They are basically evacuated tube solar collectors. So it's very easy through the collectors. I'm using 8 collectors. And then you can easily get an air temperature of 100 degrees centigrade, very easy. But it's very easy to lose it because air has a small specific heat. It cannot keep the heat. Water has a specific heat of 4,000 plus. So when I'm heating the water, the hot water can penetrate easily in the pipes, especially if the pipes are insulated, so you can keep the temperature of the water high. Air, you have to have bigger diameter of the pipes, and the power needed, the fan power needed to draw the air or to drive the air is going to be higher than the power needed to drive the water in tubes. If you remember from our study of the thermodynamics at the beginning of the semester, we were talking about the pumping power for water versus air. And basically it's the integral of a specific volume into delta P. The specific volume for the water is very small. For the air, specific volume is large. That's why it needs larger power to drive air into tubes. Water is much easier. Water is incompressible. It has high mass density, so you need small pumps. Tubes are having small diameters, and pipes are available even in PVC, which is basically an insulating material. The problem with water is that it freezes during winter temperature for cold climates. And freezing, water expands upon freezing, which means that it may damage the collector. So you have to do things for that. And there are 2 solutions for the issue of freezing. One of them is just use an antifreeze, like the green water that we buy for the radiators. This is basically some sort of ethylene glycol, and the ethylene glycol has, a solidifying temperature which is well below 0. So I mean, you can reach 0 and still you don't have to worry about the water in your car, and you should not. Another solution is to have your system, whenever it's coming up to a threshold of temperature for the air, it could be either lower solar radiation due to the very cold day and very cold weather, and even with clouds in. So what you have, your system is going to evacuate the water. So the water is stored in a tank. And whenever the solar radiation are a little bit higher or the sun is up, then you can recirculate your water again. The antifreeze is having a lifetime of about 5 years, where it should be replaced after that. Otherwise, its chemical stability is going to be affected. The solar collectors with air, if you are intending to heat the air, I mean, for us who are using it for experimentation, If we're talking about systems that we needed hot air, maybe using hot air through solar collectors can be a good solution. But they have been always used in history for drying the crops, or even for producing salt. You can see if you just pass by salt producing facilities, especially the old ones, you'll find that there is a large surface area where they are putting a shallow depth of seawater there, and they leave it to evaporate, and then the salt will be left there. So we're talking about drying here of crop, or even drying or obtaining the salt. You may use fans or blowers to drive the air in. We're just talking about this issue that using the fans is costly because fans require more energy compared to the pumps. However, there are some of the collectors that are using the buoyancy effect. As the air heated, it becomes lighter and it tends to move upward. And as the air cools, it tends to move downward. So you can create a cycle of recirculating air or even water where you don't need a pump or a fan. You are just relying on the difference in the density due to the temperature. The fluid gets heated, it is lighter, it tends to move up. When it gets cold, it's heavier, it tends to move down. So you are creating some sort of a natural circulation. The natural circulation is slow, the heat transfer coefficient is small, but sometimes for some applications that's good enough. The unglazed solar collectors with no glass cover, they are there, and normally they are used for low temperature applications. We just mentioned swimming pools, and they are very common for indoor swimming pools heating, that they use that solar collectors to do that, or even outdoor pools. Pools are not only like that, but sometimes the pools are covered, especially in winter, so that you are reducing the evaporation. And if the pool is being heated by solar energy, then you are as if you are storing your energy in it so that it does not cool down quickly. So this is for low temperature applications like swimming pools, preheated water, warming water for aquaculture facilities, and heating for showers and camps. All of these would be fine to use cheap solar collectors, which are the unglazed ones. They are fabricated from channeled panels of plastics. So basically they are plastics, black, so that they absorb energy as much as possible. And they are efficient in the sense that there's no glass, so they are cheap, and you are not losing part of your solar energy by passing through the glass, through a glass transmissivity of somewhere between 80 and 90%. Ambient air, if you are talking about warm air, the warm air can transfer its energy to the air inside the unit or the water inside the unit, so it can be a source of heat as well. Although this is not really a reliable source because the ambient air temperature can vary through the day, but it can be a positive part for even some of the time of the day. Sometimes refrigerants and phase change liquids are used. Why? Because they are boiling at low temperature. They have high energy density through the phase change. I remember one of the experiments that we have done. We were doing a collaboration with MIT for about 8 years, from 2008 up to 2016. And during that, one of the parts that we worked on is manufacturing of an air heated solar collector that has its storage built in. So basically we had to use paraffin wax, and the wax was below the absorbing unit or the absorbing surface, the absorber of the solar plate. So we have air passing on top of it and wax at the bottom. What would happen? As the solar energy is there throughout the day, it heats air in the solar collector, and definitely first it heats the absorber surface. The absorbing surface from the other side, it is connected to it touching the wax. So the wax is going to get heated, and the paraffin waxes start to melt at temperatures somewhere between 40 to 60 degrees centigrade. So in a couple of hours, maybe during the day, you can melt all the wax. It will melt and probably be a little bit heated over the melting temperature. And then after sunset, what would happen? No further energy added to the unit. So the salt or the wax, I'm sorry, starts to cool down. Cooling down, it means it transfers its energy to the air which is passing on top of the plate. And then it starts to solidify. As it is solidifies, it is releasing its latent heat of fusion. And accordingly, what would happen is that, again, additional energy is being transferred to the air. So you can keep your air heating maybe a couple of hours after sunset by just having the storage in this unit. Selective surfaces are another very good facility for the absorber plate. The absorber plate it is covered with a black surface, and it is basically absorbing most of the energy falling, not all of it, definitely. But having a selective surface, which is a layer treated on the surface of the absorber, is going to make a difference in the amount of energy which is being received by the absorber. So absorbers are basically thin metallic sheets with excellent thermal conductivity so that you can have homogeneous temperature across the unit. Aluminum is very common material used for that. The upper surface is painted by black. The solar absorption is about 90%, which means that 90% or 95% of the energy falling into the unit is being absorbed and converted into heat to heat the plate. The surface emittance also is high, and this is the problem. A black surface can absorb most of the energy falling into it, but it transmits most of the energy that it has as well. So it's easy to heat and easy to cool. What we need a surface which can be heated up easily, but it will not lose its heat. And this is basically what's meant by the selective surface. You are talking about a surface that has an absorptivity of 90%, 95% or more. The higher the better. And the emissivity, it does not emit solar radiation. The emissivity is on the very low side so that it maintains the energy within it. And this is basically what's meant by a selective surface. Again, a selective surface receives most of the energy falling into it. It absorbs the energy so that it is heated, but upon heating, it does not transmit the energy as the nature of black surfaces that transmit most of the energy out. No, it keeps the energy in it by having low emissivity. It needs special fabrication to produce a surface with high absorption and low emittance. And these are basically what we call the selective surfaces. The absorbing layer is several micrometers thick. Actually, thermal radiation is like convection. It's a surface phenomenon. It's something which is occurring between the surface and the surroundings. The surroundings could be a gas or a liquid. In the case of convection, for radiation, it's gas, liquid, or vacuum. It is supported by that it's providing a thin polished metal surface. There's a special type of polishing that keeps the emissivity of the unit low. When it comes to connection of the of the flat plate solar collectors, here we have a sample of supply cold water or supply water from the collector, which are hot, and the return water, which is cold. Normally, it's going through a cycle. The collector is heating water. The hot water goes into a storage tank, and then the storage tank absorbs the heat from this water, so the water becomes cooler. They go back again to the solar collectors for heating, and you have a closed cycle like that, and you keep on doing that until the absorber, the storage unit reaches to the required temperature. You can replace the storage unit by a load, or you can have the storage unit and then the storage unit is connected to a load where you have constant temperature from the storage. What we see here is some sort of asymmetric kind of connections across the flat plates. Look at the supply, look at the return, you'll find that they are symmetry, the same length of pipes, and this is actually is being meant as a good design for the unit, so that you can have some sort of a balanced operation of the unit. You don't have some sort of very long tubes on one side, short tubes on the other side, so it goes out of balance in terms of the amount of energy which is carried by the water as it passes through the tubes, in or out. The flat plate collectors are connected normally in parallel. Why? Because we need to have the heat transfer fluid flowing through each collector at the same rate. We're talking about a balanced thermal flow and characteristics for every collector. That each collector should have basically the same efficiency. So we can talk about the same efficiency value for the whole system that we have. So we maintain the same flow path in each collector, same length, definitely same materials. This is a cutaway view of a flat plate collector. And you may see here as the solar energy passes, it penetrates through the glass. The glass has a transmissivity. It falls down. This gray thing, basically, it should be a black surface, which is the absorber. It gets heated. And then we have tubes that are mainly made of copper, because copper has a very high thermal conductivity, that are connected through a header. So I have a header here where the water comes in. Then the water is going to be distributed from the header into these tubes, where it will be heated, receiving energy mainly by being in contact with a hot absorber plate. And then after that, it is collected in another header, and you are going to take your hot water out of it. Normally for flat plate collectors, the inlets and outlets are something like, I remember the units that we have. We recently bought a couple of units of flat plate collectors, and I think there are 4 units that we bought. We have connected 2 of them. Again, this is all in our research area in the beach facility. And the outlet here, I'm trying to recall, I think it was something like either a 3/4 or 1 inch diameter pipes, metallic pipes. And after that, you collect, either you continue with metallic pipes, which are costly, but normally what we do, just use a connector, and then we connect our PVC systems. PVC is especially the light gray type. It can withstand temperatures up to 70 or 80, and you don't have really to insulate them, because PVC has a lower thermal conductivity anyway. These are layouts of flat plate collector connected to storage. And the figure in the left is interesting because it is considering the effect of buoyancy. When you look at it, there's no pipe in the system. What you are doing, you have a solar collector, and the solar collector here is heating the water. The hot water becomes lighter, and on the other hand, there is cold water here, which is heavier. Flow of the cold water here pushes the hot water above, and then you are having some sort of a natural circulation here. It is not necessarily water, by the way. You can have special heat transfer oils in here. Especially that if you are interested in water heating, what we have here is some sort of an indirect heating, which means that this heat exchanger, which is the hot water storage tank, basically has cold return from the load. The load could be, for example, an air handling unit in a house if you are looking for heating, or it could be direct utilization. For example, people are using the hot water in washing or in showering or whatever. So the cold water and the hot water that are for domestic use are going through the pipes in this unit, whereas the shell side is having this fluid which is coming from this, and both fluids are not mixed. So it could be like that, especially if you are going to put ethylene glycol with the water. You don't want the ethylene glycol to go to the hot water supply to the space, but rather you put a heat exchanger like what you see, the one in the right here. You have the heat transfer fluid is going into coils, whereas the domestic hot water is going through the shell side of that heat exchanger. So it'd be something like that. There are classification of of the storage units as well. That could be either a mixed type or a stratified type. By that, I mean we can assume the whole storage is at a certain temperature, or it can be like stratified in a way that it is layers, and each layer is characterized by a certain temperature. It depends on the design. What we have in the left is a system that does not need a pump, and that's why we call it a thermosiphon collector. Whereas in the right side, we are talking about a pump which is circulating the water through a closed cycle here. The water gets heated in the collector. It goes here, it transfers the heat to the fluid which is around it, and then it gets colder, it goes back again to the collector to be heated, and the cycle is closed, so it repeats itself this way. This is flat plate collectors that are used for pool heating, and some sample could be like this. You have a pump which is basically driving the water across a coil, and this coil does not have any glass on top of it. It's just without glazing or unglazed solar collector. It heats the water, and the hot water will get into a tank, or it will get into the pool right away. Lately, in the last few years, just recently, another type of flat plate collectors, which are basically hybrid PV thermal collectors, are there. What we have in front of us here, it is not direct heating from the sun to the tubes of the water. But basically what happens when you have a PV system, the PV panels are receiving energy from the sun. They are converting this energy into electricity, but they have an efficiency of about 20%. So 20% of the solar energy is converted into electricity. What about the 80%? It's converted into heat. So the panels are heated. The problem with the panels is that their efficiency reduces when the temperature increases. So there have been research in the last more than 10 years ago to effectively cool the panels, and people used lots of things. Some used like tubes passing on the back of the PV panel so that they can absorb the energy and keep the panels cold. People, especially in a group in our university, have started to use some sort of jet cooling, like they have water sprayed on the back surface of the tubes, and spraying would have a high heat transfer coefficient, so it does effective cooling, until these units came to the market, where you have basically a coil which is made of mainly of copper that circulates, and it is connected to the back of the panel. It is connected through a thermal grease and absorber plate. So the absorber plate gets heated. It is through the thermal grease, it is in direct contact with this unit. There are no air pockets, so it is receiving the energy of heat that has been absorbed by the PV panel, and then it uses that heat to heat water inside these tubes, so that the panel itself gets cooled because of the cooling effect here, and the water gets heated, and you can make use of that. Actually, one of the latent breakthroughs that a group has done in KAUST in research is that they have used these units to create electricity and use the heat coming from the water outside of these tubes in a membrane distillation unit for water desalination. So they are producing electricity, and they are desalinating water at the same time. This is, again, one layout of such a system. You have a PV system, which is on the top here. This is connected to batteries for energy, for electric energy storage. On the bottom, you have the heat, the flat plate collector, the tubes of the flat plate collectors that you see here, and they are connected into a water heating load, which means that you can do domestic water heating and electric generation at the same time. Definitely, these collectors are expected to be expensive because they are just recent, but I think that with more manufacturers and more consumption, eventually the prices are going to get down with time. Evacuated tube solar collectors, on the other hand, is another kind of application. Why evacuated tube? This is basically is made up of a double layer of glass, and this double layer of glass have evacuation in the middle, so there's vacuum between them. Glass is going to transmit the solar energy anyway, so the energy is going to penetrate whether it is one layer or two layers of glass. Solar energy can penetrate in a medium, or can it penetrate in vacuum? So it will penetrate through the glass anyway. But why evacuated? The reason is for evacuated tube, vacuum means no medium. So there is no energy loss from the collector to outside by convection. So basically, you are maintaining your fluid inside at a higher temperature. And evacuated tube collectors are the ones that are used whenever slightly higher temperature is needed. If I'm talking about a flat plate collector that can heat water up to 70 or maybe sometimes 80 degrees centigrade, so going above 80, maybe to 120 or so, this can be done by evacuated tube collectors. How this is done? By preventing energy loss from the collector. Now you are eliminating any energy loss to the outside, and you are keeping all the energy inside. Prices are not very expensive if you compare the flat plate collector and the evacuated tube collectors. Evacuated tube collectors are normally something like 30 to 40% more in price compared to the flat plate collectors. And actually, there is a large variation when you go from manufacturer to another. Maybe you can get a Chinese evacuated tube collector by the same price of a flat plate collector coming from Europe. So it's not really a substantial difference. Definitely the quality will differ, but the prices are comparable. We expect higher efficiency, especially at high temperature. They do not lose the energy easy. Flat plate collectors are basically receiving thermal energy. They have very high efficiency, but the efficiency gets less quickly as the temperature difference increases, which is not the same as evacuated tube collectors. We'll see a figure now that's going to show that. The problem with flat plate collectors is if you are using it in very cold climates where snow is falling, the collectors are not penetrating the energy outside. So the surface of the collector remains cold. So if you have ice accumulation on the collector, you cannot get rid of it easy. A flat plate will get heated, it will transfer energy outside, so the ice melts, but not for this kind of collectors. Then you have to be really careful when you are using. We are not worried about ice formation in Saudi Arabia, but in places where ice accumulates, in Canada, it can accumulate to something closer to 2 meters high. So flat plate, the evacuated tube collectors might not be the right solution for this kind of environment. This is what you see. There is some sort of a tube where vacuum is there, and you have an absorber plate inside. Energy is going to go down, to go from the air. It doesn't have to be a double glass, by the way. But this is going to be more expensive when you're having something like this, because all of this has to be kept in vacuum. And the glass has to be robust enough so that it can withstand the difference in pressure, which is into the area. It's a difference. It's a force acting on the surface of the glass. So you have to be careful when you are using these units so that they don't break. So energy is flowing from the sun. It will penetrate through the glass transmissivity. It will fall into an absorber plate, and the absorber plate is going to heat fluid inside the tubes. This is one layout. And because there's no medium here, there's no convection losses to the surface. And definitely there's no radiation losses to the surface because we're talking about greenhouse effect. So the long wavelength radiation does not penetrate through. So it's only energy in this case, and the energy out will be the water that heats up and leaves the collector. What we see here basically is a cross-section of the tube. This is a layout of different types of evacuated tube collectors that can be installed on the ground, or they can be installed on the top of buildings. And here roof mounted, the roof is horizontal. That's why you need a stand. But if the roof is slanted with a slope, you can just put it on the roof directly, like the figure that we have seen earlier, considering the flat plate collectors that are on the roof. Flat plate collectors, the evacuated tube collectors can have different layouts. In some of them, we are using a heat pipe. What's a heat pipe? Look at the figure here above at the right. What we see here is a heat pipe. It's a sealed pipe which is made up of copper, and this sealed pipe has a bulb out of it, a part of it outside. This part is inserted into a tank. So actually these are plates that are having a tank on top of it, or at least it will have a header like this, a manifold like this. So this part is situated in the middle of this manifold inside here. So the tubes here are inserted into openings, and they are bringing this manifold or the top of the manifold here in the passage of the water as it passes in. What happens here? We have a special fluid inside. The special fluid, when it is exposed to the sun, it evaporates, and the vapor is going to move up here. And as it moves here, what will happen? Water is going to go through. So the heat transfer will take place from this vapor to the water which is passing through. So the vapor will condense into liquid. So it will fall down by gravity. It will be heated by the sun, evaporate, go up, cool down, condense, go down. So it keeps up and down all the time. As if you have something vibrating up and down all the time. Then this bulbs or the ends of this heat pipes are situated either inside a tank, so you can have a built-in evacuated tube collector with its own tank, or you have a header here where basically the flow of water or air, the fluid in general, is passing in, and these units are always hot because when they condense, they will go down. It's a very quick process. They will go down, they're heated by the sun, evaporated, going up. So it's always a hot or a source of heat for the water which is passing through. Normally, these collectors you can find it in 10 tubes, 20 tubes, 30 tubes. Some manufacturers are bringing units with 16 tubes, so there are different designs for that. And there are so many manufacturers for evacuated tube collectors. Do all the evacuated tube collectors are having heat pipes? No, not necessarily. This is one common design. But another design is, and this is what I was talking about a while ago. You have an evacuated tube collector, which is just installed on a slanted roof, or some of them are having the stand and they have their own tank as well. So this tank is as if you have energy heating and storage at the same time. The units, or we have both of these in our facilities here that I've been using. Like the first set of collectors that I bought, they were basically flat evacuated tube collectors to heat the air. So they basically, we don't have a tank. It was just a manifold like this where cold air comes in here and then hot air comes from the other side. Lately, for water heating, we brought evacuated tube collectors that are having this tank on top of it. The last collectors I bought were basically flat plate collectors with tanks built in like this. This is another layout. You can see here, this is the double glass. The vacuum is that gray thing here. This is where the vacuum is applied in this area. And what would happen? The tubes are coming in a U shape inside here. So cold water will come in, it will get into this area, and it will be heated and it will flow outside. So we do not have a heat pump for this case, but this is direct water heating or even air heating in these units. It can be like this. The air heating units can be slightly different. I think the ones that I have or that I first bought, they were evacuated tube air heated system, and the layout for this system was you have basically an evacuated tube. Let me see if I can plot it here. This is basically how it looks. And this part here, sorry, in between is basically where the vacuum was. So this part inside was where's the vacuum. And here you have just a tube like this. That's it. And this is connected to a manifold. And the rest of it is connected to another manifold like that. So what would happen is air comes here. Sorry. Air gets in here. It will pass through this tube, and the tube from the end is open. So air is going to go through this concentric area, and it will go up. So you have heating for the air as it goes down and goes up, because solar energy is directed here and it's passing through. This tube is made of aluminum. Sometimes you can have this tube painted by black, so that it gets heated. It heats the water as it flows down, and it heats the water as it goes up, and the hot air is leaving from here. So you have cold air in here, hot air out here, and the units that we have are basically 20 tubes in operation, and I mean connected together in parallel in a system which is very much the same like this. So that you have an inlet here that will pass inside the tubes, and outside it will go out, and then it will leave as hot air, as you can see it here, from the concentric part, which is the outer part of the inner pipe. And this is basically is what we have here. These tubes are made of aluminum, which is very much the same. It is similar to the one I sketched a while ago, the one that you have here on the right. This one, you can easily get high temperature of the air. Air has a low specific heat. It needs a small amount of energy to heat it up. But as I mentioned, the problem that we faced with this kind of layout is that, number one, because it's air, we had to use like a 4-inch tubes. It's not like the water. The water you can use 3/4 of an inch, and that's fine. But 4-inch tubes here, and it's very easy to lose the energy. If the tubes are going into a tank, then definitely in the expansion part from the tube to the tank, you can find there is a big loss of temperature.
Excuse me, Doctor, I have a question here.
Yes, go ahead, please.
As you know that this is the U-pin, okay? The water flow in the U-pin will be very fast. So here we are talking about the water flow will be in a millisecond, okay? So I cannot imagine how the water will get to be heated in these milliseconds, okay? And what's the percentage of conversion of the water? So what's the cold water temperature and at the inlet, and what's the hot water output, okay, temperature?
If you are talking about this arrangement, then basically, when you are having a system which is made up of 20 tubes, the flow rate of the water is divided by them, which means that the m dot, the mass flow rate that passes in here, is small. If you recall the equation, which is talking about Q, the heat transfer rate, which is given as m dot Cp delta T. Q here, if we are talking about a solar energy in the order of 800 watt per meter square, and you can calculate how much is the area. The smaller the m dot, the bigger the delta T. So having lower flow rate of the air is going to make sure that it is going to leave at higher temperature. And then it depends, are you going to use a single collector? No, you are going more than that. So basically, you have collectors that are connected. Whenever the collectors are connected in parallel, you are dividing the flow rate over not only the number of tubes, but number of collectors as well. And when per each tube, when this value of m dot decreases, then the delta T decreases to the extent that as the water enters at a temperature of, say, 25 degrees centigrade, it can leave at 125 degrees centigrade. It looks like surprising, but this is what happens, because basically you have eliminated the losses to the surrounding. There's no convection or radiation losses. So all the energy in after passing by the transmissivity of the surfaces is going into heating of these units right away.
So we are talking here about high efficiency system.
Exactly, yes. By high efficiency system, I'm talking about an efficiency in the order of 55 to 60% for the evacuated tube collectors. For the flat plate collectors, it starts with something like 72 to 80%, but it degrades easily for the flat plate collectors compared to the evacuated tube collectors.
So, and this is what available actually in the market, isn't it?
Yes, yes.
Okay,
This is
thank you
what
very
we see
much.
in the market. This is providing us here the output from an evacuated tube collectors in New York. These are experiments that have been done over 4 years, from 2011 to 2014, complete 4 years, and the average values are being given for the output from these units as well as the input energy falling in. So definitely in months where there are higher solar energy, we're talking about May up to September, there is substantially high performance of these units. The output is high, whereas in the winter time, it starts decreasing from October up to February or March of the next year, where you can find there is a small performance. However, when we are doing the analysis, we are doing it on an average base. The evacuated tube collectors, in many cases, are located at the roofs with sealed fluid loop. So we're talking about a closed loop here. You are mixing the water with glycol to avoid freezing, and it transfers heat to a storage tank of a resident place, and you are dealing with your storage tank as a source of heat. You are passing your domestic water in for heating, and then you are taking it out as a hot water. This is a performance case study for these layouts, talking about the energy, the rate of energy transfer, which is measured by having sensors in the pumping and the control subsystem. Definitely what you need there in a system like that is thermocouples, flow meters, and pressure measurement devices, so that you can measure how much is the flow rate, what is the temperature across the solar collector, and how much is the pressure difference across the unit. And these are basically the kind of information that you can find in the specifications of a flat plate collector, in addition, definitely, to the efficiency curve of that collector. So we have cumulative energy being delivered to be calculated in kilowatt hours. The peak performance is normally found in the afternoon hours, where basically this is the highest solar energy falling into the unit. And there is a capacity factor, which is calculated by comparing the 4-year average annual output with the productivity that could have been obtained if we are maintaining constant temperature in. The ideal conditions for testing for the manufacturers is you have a water flow in at a temperature of 20 degrees centigrade. And with a certain amount of flux, the one which is given here is about 428 watt per meter square. So you just based on that see if all the water is coming at constant temperature of 20 and you have a steady solar collection of 428 watt per meter square, then this is what you expect to be obtained in a clear sky. Now you can compare basically what you are getting actually from collector that you have in terms of flow rate, in terms of temperature difference, and time of operation, so that you can calculate how much energy you are getting from the collector. You divide it by the standard, and it gives you what results in what we call the capacity factor of that solar collector. An example here, talking about a collector size that's going to operate for a certain number of hours. A year would have 8,760 hours. And if it is producing 2,039 kilowatt hour per year, then it's about 14%. So going back again to this specific example that we had in for the operation of the plant or the solar collector in New York, they have made an average of the operation in the 4 years and calculate how much energy is being obtained or used for heating the water in this collector over the 4 years. And then after that, seeing how much is the energy falling into the collector and what it should have been produced if the inlet water is 20 and for a steady operation with solar flux of 428, and the ratio that's been given here showed that a capacity factor of 40% has been obtained. If we are talking about sizing of solar collectors in a place or in a house that has 4 persons or n number of persons, then the standard rate is 100 liters per person per day. So if we are going to make or come up with a solar collector system, then your values should be around this. How many persons are there? And then you can estimate how much is the total heat or total rate of heat of water that's to be heated per day. And it depends on the number of persons accordingly.
So, Doctor,
Yes.
One collector can heat how many liters?
The flow rate. Now, the point here, the answer is I cannot give you a number for this because it depends on this collector is having a flow rate of what? What's the flow rate of the water in and how much energy it's been exposed to. A collector here in Saudi Arabia may do a work that is equivalent to 2 or 3 collectors in other places of the world. So now it depends on how much is the energy falling into it and how much is the water flowing here. You have an energy coming in, which is basically the solar energy flux multiplied by the surface area of the collector. This is the energy in. And the collector has an efficiency, say 70% or 80% of this energy is going to be converted into heat. This heat is m dot Cp delta T. So what is the inlet temperature and what is your target temperature, and accordingly what's going to be the flow rate. So there's no a single number to answer your question, but it has to go through that energy balance.
Okay, Doctor.
Now,
Doctor, I have other question here.
Yes, please.
So now the solar collector, okay, يعني if you put it in Saudi Arabia, it's different than if you put it in Canada as an example. The hot water here is the hot weather is too much. We need the solar collector actually in the winter more than the solar collector in the sun and during the summer. So يعني this efficiency was measured during the summer or during the winter side. Because if you
see here,
the
now,
water I don't need يعني hot water during the summer. I need it only during the winter يعني if I'm going to use it for domestic.
Yeah, when you are talking about efficiency, you are basically talking about how much is the or how much the value of the efficiency. It's not a constant value. You cannot say that I have a solar collector that has 80% efficiency. You should say I have a collector that has this amount of efficiency at this temperature difference.
You're right, yes.
For example, when we are talking about, we will see the efficiency curves. You have something like this, efficiency versus delta T, or in many cases is delta T over I. I is the incident solar energy, and delta T is the temperature difference between the outlet of the collector and the inlet. So, and the inlet, for example, sometimes even people use the inlet as the air temperature around, because basically water is expected to have the same temperature of the air or close to it. So efficiency versus delta T over I is the efficiency curve of a collector. And for each manufacturer, it should provide this figure as a figure, or sometimes if the relation is like this, this is for evacuated tube collectors, and this is going to be for a flat plate collector. So if you have this kind of temperature, you may go for flat plate collector. If you have this kind of temperature difference, you go for the evacuated tube collector. So now the efficiency depends on how much delta T, how much temperature difference you need to rise the water, and how much definitely is the solar energy which is falling here. If the solar energy is high, the delta T is low, so you may go to this area. So the efficiency of your solar collector is going to be much higher in Saudi Arabia compared to if you put it in a cold place. I hope that temporarily answer your question, and then we're coming into this again when you are talking about the efficiency.
Yeah, Doctor. Okay, thank you.
So when you're talking about 4 persons in a house, and each one would require 100 liter per day of hot water for household applications, then that would be equivalent to 16.7 megajoule per person per day, and using standard input and output temperatures. So the requirement for 4 persons are going to be this number multiplied by 4. You can calculate it per day, and then you can calculate it per year, so that you can estimate the annual requirement of a person and then of a family over the year. This number definitely changes with change in the climatic data, because the ambient temperature and the water temperature is not the same. It does not only vary from one place to the other, it varies for the single place, from a season to another, and from an hour to another within the day. And these things have to be taken into consideration when you are calculating or when you are sizing the correct or the right type of solar collector for your application. Do you have a space on the rooftop or not? If not, then we have to put it on the ground. Putting it on the ground, we have to make sure that it will not be shaded by trees or by other buildings. Not only now, but you should keep in mind that hopefully in the future, no very tall building is going to be erected next to you so that it can cover or it can shade your collectors, and that's another issue. The collectors have to be well insulated so that you are conserving your energy. You are not losing the energy just by heat loss to the surroundings. Shall we have like a 5 minutes break, and then we'll come back to continue, inshallah. I hope today's class is going to be interesting. Actually, I did it in a way that we are going to end up with an exercise that would enable us to size any heating system, any water heating system. And I just brought one example that I found in a paper, and I did it in details. I'll be sharing with you as the last part of the class today, inshallah. So 5 minutes, and then now it's 9:35 in front of me, so 9:40 we'll resume, inshallah.
دكتور عنتر،
تفضل.
بس عشان اتاكد، هذا الووتر هيتنج فور هيومن يوز، رايت؟
Yes. So back again to the issue of solar collectors. Yeah, now we'd like to have a look at the energy balance, like heat transfer in flat plate collectors. The energy balance, basically by that we mean the difference between the incident energy, the energy that falls on the collector, and the heat losses back to the ambient. Because the difference between them is the amount of energy that the collector is going to use to transfer to the fluid inside. Considering the steady state applications, the useful energy is basically, as you can see here, this is the difference between the falling energy. Tau is the transmissivity through the glass. Alpha is the absorption of the collector receiving surface. This is the solar energy, and this is the area of the collector. So this is the incident energy. This is the falling energy into the collector. And the losses to the surroundings are given in terms of an overall heat transfer coefficient into the area, into the temperature difference. This difference is being utilized to heat the fluid that has a certain capacity from an inlet temperature to an outlet temperature. So again, this is the useful energy, the falling energy, energy N, minus the energy lost out. The difference between this is going to be utilized in heating the fluid in. The efficiency basically is talking about how much is this energy compared to the energy falling from outside. The energy received from outside is basically I into P. This is the total insulation I into the area. This is the insulation, the insulation falling on the surface of the collector. So if you divide the QA divided by I, AP, this is what we get. I into AP in the first term will cancel out, so you have tau alpha. And the second term, the AP will cancel out, so you have UL delta T or TAP minus TA divided by I. The absorber plate temperature, however, is difficult to determine. Normally, the plate temperature is not necessarily homogeneous. We try to make it homogeneous or uniform by using aluminum, for example, as a material, because aluminum has thermal conductivity, and the higher the thermal conductivity, the smaller the temperature difference between the locations. But remember that there is a fluid passing through, and at one end, there is cold fluid in, and the fluid temperature increases as it passes through the pipes. So the average temperature might not be exactly the same for one place to the other within the collector. There are locations where they are connected to the pipes and locations where they are not. So talking about a precisely homogeneous temperature for the whole plate, it's not practical. So how many thermocouples should you put in to measure it? So that practically speaking, it's not something easy to get, the issue of the temperature at the absorber plate, which is TAP. That's why there have been a proposal by ASHRAE, which is the American Society for Heating, Refrigeration, and Air Conditioning Engineers, who proposed an empirical adjustment factor that's called heat removal factor, FR, to this unit. So the unit that we have here, or the equations that we have here, it is simple, it's straightforward, but we have an issue with the TAP, T absorber plate temperature. So that to overcome this, we are going to follow what approximation that ASHRAE has been done. So it's talking about QU, the useful energy. We are using here the value of FR. And as I mentioned a while ago, FR is what we call to, or what we refer to as the heat removal factor. So the Q is given in terms of heat removal factor. And the heat removal factor being added in allowed us to change the temperature difference. And instead of temperature of the absorber plate minus TA, it is TI minus TA, where TI basically is some sort of inlet temperature. Interpretation here, the ratio of net heat actually collected to the net heat that would have been collected if the entire absorber is at an inlet temperature TI. This efficiency data are plotted against the TI minus TA over I, which is the incident solar energy N. And then this is going to be curve fitted using regression, whether it is given in a linear or a quadratic relations. And you will find that every manufacturer who is producing solar collectors should provide a sheet, and in a specification sheet, and in the specification sheets, it should give these values, which are the FR. When you look at this expression here, it looks like a linear relation. And this is the intercept with the y-axis, FR tau alpha, and this is the slope. So, and basically what you are plotting efficiency, which is eta, that has been plotted here. It's been plotted versus Ti minus Ta divided by I. So this is our y, and this is our x. And this is A and B. A is the intersection with the y-axis, B is the slope. So the values of A and B, the intersection and slope, should be provided by every manufacturer, not only every manufacturer, but sometimes some independent agencies are doing testing for collectors, and the users would not accept for their buying unless it is certified by an independent entity. And this independent entity is providing sort of certificates or specifications that are going to be published and used for all of the major manufacturers doing that. So this is our y, this is our x, and then this is the slope, and this is the, this is the intersection with the y-axis, and this is the slope. So these values, Fr tau alpha, Fr UL, are the values that should be provided by every manufacturer. Sometimes they give the values, sometimes they give the values and the plot as well. The single glazed collector transmits more solar energy to the absorber plate, but they are less insulated against heat losses to the surrounding, so they may have a higher intercept but bigger slope. The reverse is for the double glazed, and that would probably explain the figure I plot a while ago, where for flat plate collector you can have an efficiency which looks like this. Here we have Ti minus Ta divided by I. This is the intercept, Fr tau alpha, and this is the slope, Fr UL. And another collector would be like this. Selecting this one or this one, it depends on the applications and the temperature range, or actually delta T over I that you are in. If you are in this area, go for this one. If you are in this area, you are going to go for this one. It has higher efficiency. That's why it's not a surprise when we did some sort of an extensive study for the utilization of solar collectors for water heating in the domestic sector. By the domestic sector, I mean hospitals and hotels. That we did that study over in the major cities of the kingdom, and it was not a surprise that all what we got basically was a recommendation for a flat plate collector rather than an evacuated tube collector, because basically, because the water temperature is not very cold, even in winter, then we are always in this area. So the flat plate collector efficiency is higher than the evacuated tube collector, which is the double glass one. Fittings sometimes are used. You can find these equations that are given. Some people would say that this is pretty much the same, looks like a linear relation. Some other would say, no, it's not really linear, but the line has certain sort of curvature. So why don't we give like a second order equations? And you'll find also manufacturers are providing you with these values as a first order or a second order equation, and you can use whatever is suitable for you. If you are okay with the first order analysis for a straight line formula, then you can use this one. Otherwise, if you are more meticulous and you want to get, you see that it's not really a linear relation, but it's look like a second order relation, you have this there. And these coefficients of B naught, B1, and B2 are always given. Again, B naught, it looks like Fr into tau alpha. B1 is Fr into UL for the, if you compare it simply to the equation that we have shown earlier for the energy balance.
Sorry, Doctor, what is Ti minus Ta?
Excuse me, Ti is the inlet temperature to the collector. Like inlet temperature of water coming to the collector.
What about Ta?
Ta is the ambient temperature, and this is basically, there's some sort of a differences between the American standard and the European standards here. Some of them will take the inlet temperature Ti. The European standards are taking the value of Tm. It's the mean temperature between inlet and outlet. So again, the kind of figures that are given, you should be careful. These figures are following which standard, American or European standards.
Okay, thank you.
This is the figure here between the single, shows that the efficiency of single glass versus double glazed collectors. And this figure is got to be there whenever you are, maybe in the next break, I'll try to find one of those sheets that have been given by an independent entity. And we use those sheets as a proof of the performance of certain collectors. There are hundreds of companies that are producing solar collectors. There are big ones. For example, I remember there is a very famous producer called Calefi that actually is producing solar collectors for decades. It has a factory in Italy, definitely, and factories in the States. So it's producing here and there. On the other hand, there is a very famous German producer, which is called Weissmann, and its collectors are very much efficient. They are very good, but they are more expensive. And there are definitely other collectors that you can find in smaller shops in China, where you can get your collectors at a much cheaper price. All you have to do is just visit Alibaba.com and just look at the solar collectors there and their corresponding prices. When we are talking about the kind of solar energy falling in, there is a critical value for the insolation that would vary through the day. Definitely, we know that the value of the insolation changes through the day from the sunrise to the sunset. The area under the insolation curve is the total energy available for the collector through the day, which is the area basically is there. What is available is the amount which is available for collection, which means that this is some sort of the solar energy that we can make use of, and this is the quantity that is being lost, you cannot use. Accordingly, a figure like that for a certain collector will tell you how much you can make use of in terms of energy falling from the sun. We don't normally go to a figure like this whenever we are doing sizing for a solar collector for a place, but this is just some sort of information that relates how the collector is performing in this kind of weather condition. The standard testings are based on instantaneous energy. That's why the collector efficiency can be an instantaneous efficiency at this time. What is the delta T and what's the efficiency? And this efficiency may change as the temperature difference changes. Energy available for capture is the integrated solar irradiance. The energy captured and made use of is that MCP into delta T, T naught minus Ti, T outlet of the collector minus T inlet to the collector. This is basically how much energy has been transmitted to the fluid that is being heated. So the efficiency is essentially how much energy you are capturing divided by how much irradiating energy is imposed by the test facility. And tests are being done in not necessarily in a solar, real solar energy kind of operation, because waiting for a day of clear sky and days with different temperature, that's something which is not easy to get. So what they do, they try to mimic everything in the lab by having special incidence lamps that are resembling the solar energy, and they have their labs at controlled conditions in terms of weather conditions, air condition in the lab, temperature of the air, and even the temperature of the water in and out from the collector. It's not only the thermal performance that is going to be considered but also the shock resistance, the static pressure characteristics, which should be given. How much is the pressure difference across the collector, so that you can size the right pump that's going to pump the water through the collector. Collectors with very thin tubes might need higher pumping power because the friction is higher. Bigger tubes, lower pumping power. So this, you should be aware of this. How much is the fluid pressure drop as it passes through the collector? How much is the thermal time constant? How long will it take before it starts heating of the collector up to a certain temperature? Water heating collectors follow the ISO standards, whereas the air heating collectors are following the ASHRAE standards. Rating and efficiency curves should be published not only by the manufacturers as being written here, but also by independent agencies, which in many cases they are more trusted because they are not biased. And they are doing it for different types of collectors manufacturers. When we come to the storage issue here, solar water heaters use water as a storage medium. Water is available, it's cheap, so, and it has a high heat capacity, so it's a very good option for heating. On the other hand, the air heated systems using pebble beds, they are using like small balls of certain diameters that as the air passes through them, they are getting heated and energy is being stored in these. Some are using stones, special types of rocks. Some are using molten salt. So it depends on what is the temperature range that you are talking about and what's the size. Typical liquid storage design is for fluid flow in one side and no flow on the other side. Look at this. Here we have a storage system where the flow coming in here. So hot water is coming in, cold water is leaving. It is being heated in the collector to heat the unit. And it is a closed loop of a heat transfer fluid that is going through the collector here. Accordingly, the storage temperature keeps on increasing. What's the ideal case? The ideal case is this is coming as hot and it leaves as cold. So the storage temperature is normally close to the leaving temperature here. You need the leaving temperature to be as high as possible so that you can make sure that the storage has reached the capacity that's needed for it, and it can be used now for as a source of heat for the domestic use. The UA value of the exchanger is important. U is the overall heat transfer coefficient. Area is the total surface area of heat transfer. This expression UA is called conductance, the conductance of the heat exchanger, which is one of the parameters that are extremely important to be published by the heat exchanger manufacturers. A company producing heat exchangers should be indicating what is the UA value of its unit. So a typical exchanger may have a coil made of copper. It can be finned coils. So if we are looking for higher heat transfer area and higher heat transfer between the heat transfer fluid and the storage medium, the UA value is given by the manufacturer as a function of the transport fluid rate for a certain flow of this kilogram per second or liter per minute. Then this is expected to be the UA value. The water from the collector, which is hot, it enters the storage, and then it transfers, it heats, and accordingly cools down to a lower temperature when it leaves the storage. To transfer maximum heat to the storage, the area should be indefinite. I mean, this is typically, if we need to have all of the heat coming in to the storage, then your area should be infinity, which doesn't make sense. And accordingly, the issue of the heat exchanger effectiveness comes into the picture here. Higher effectiveness means you are able to absorb more energy that is coming to you and use it for heating your heat exchanger or the storage. And that's the expression of the effectiveness being given here. Effectiveness is Ti minus To. Ti is the inlet temperature to the storage, to the heat exchanger. This is coming from the solar collector. And this is leaving back again to the solar collector, To. Ts is the storage medium temperature. So normally, the storage medium temperature is less than those. And if you are able to increase the temperature as much as you can so that the storage temperature approaches or closer to the value to the outlet temperature, then you are approaching a value of 100% effectiveness. Typically speaking, this is not practical. I mean, you don't have, otherwise the storage has to be very high to increase the temperature to Ts. For a heat exchanger with one flow or flow on one side, this is the effectiveness of the heat exchanger, which is 1 minus exponential minus UA, the conductance, divided by m dot Cp of the fluid passing through. This effectiveness expression, for those who studied heat transfer, you'll find, if you remember, when we talk about convection heat transfer, and we start talking about the issue of rating analysis for the heat transfer equipment, we define this value, and then we use it again for heat exchangers. And the effectiveness like this is normally for one fluid side. The other fluid side could be boiling or condensing or constant temperature wall, but that would be the expression of the effectiveness used there. More and more effectiveness expressions can be found in heat transfer books. For example, you can have the effectiveness, it's not really a storage, but it's just a heat exchanger so that you have one hot fluid temperature coming from the collector. It is losing energy to the other fluid, and then it's leaving. On the other hand, you have the domestic water coming and leaving from the other collector. So this is for an energy, the one that we have here for energy storage, which means that you have a container like this, and there is energy coming from the collector, at temperature Ti. There's energy leaving to the collector to be heated, temperature T naught, and we have some sort of a uniform temperature Ts. In some applications, it's not like this, but in some other applications, it is a real heat exchanger. So you have a coil here, where this temperature is Ti, this temperature is T naught, and here you have domestic water coming in. You have cold water coming as T cold I, and it is to be heated to T cold out. And the T cold out is the temperature that you use for your domestic applications. For this kind of applications, we cannot use this expression of the effectiveness, but we have to use another expression of effectiveness depending on the type of heat exchanger. Is it a double pipe heat exchanger? Is it a shell tube heat exchanger? Is it a cross flow heat exchanger? And for each one of them, there are tables and figures that will provide us with the epsilon value. I have to remind you that this expression, which is UA over m dot Cp, is what we refer to as the number of transfer units of the heat exchanger. So that epsilon is basically 1 minus exponential of minus of the number of transfer units. This is when we plot it, how does it look like? It's an exponential relation. So we have the effectiveness in one axis, and UA value is on the other axis, and what you are getting is an exponential increase of the temperature that is a big increase in the temperature, and as the UA value increases, you are going to reach for an asymptote. A figure like this can help in sizing the storage, because you would not definitely make your storage here, because adding area is going to add the effectiveness significantly. But maybe you can stop here and say that then increasing the area more is going to cost me a lot of money, but the corresponding increase in the effectiveness is not significant, so it's not worth it. And then you can make your threshold, for example, at 1,500 watt per Kelvin, for example. It could be something like this. So we plot the heat exchanger effectiveness with a transparent fluid flow in a setup similar to the previous figure, but the mass flow rate through the exchanger here is given as 0.15 kilogram per second, and the heat capacity is Cp for the fluid. Then we can look at what would be the U values of 500 to 2500 values. So you're talking about, sorry, sort of a parametric analysis that would provide you with what we see here is a relation between the effectiveness and the UA value. If you are talking about a constant area, then you can see what's the effective U value and what is the effect on the fluid that you are using. So there are so many parameters that you can use for determining the right size of the thermal storage. Then, what we might be interested in looking at is this method. The F-chart method has been in utilization for decades as one of the standard methods that helps in sizing solar collectors for heating. The solar angle, the solar insolation, and the average weather conditions do change throughout the year. You cannot design for a certain value, for a single value, but you have to keep those changes into consideration. They are time dependent. The long-term application of solar heating system is sensitive to these changes. When you are buying a solar collector, you are not buying it for a certain specific condition in the winter, but it should account for changes all over the year and over the years as well, because weather may change from one year to the other to some extent. One calculation that represents the whole year is not going to be accurate. And definitely you're not going to go through a minute by minute calculation, because it will be just very exhaustive and there's no need for it. So the computer simulations showed that monthly calculations are accurate enough without having to go through excessive computational time. Why? Because the average calculations are consistent on a monthly basis. And that actually was what is behind coming up with this method, which is called the F-chart method. There are so many softwares that are available in the market that are doing the analysis using the F-chart method. But understanding how does it operate, or how does the F-chart method is all about, is a fundamental thing as you are getting into this kind of analysis. The F represents a fraction of heating load provided by the solar heating system for a given month. It applies to water as well as air heating systems. It needs two-dimensional parameters, X and Y. One of them considers solar energy collected in a month. The other is talking about the energy loss from the collector. So one of them is interested in how much is the energy in, and the other is how much is the energy out of the system. Dividing by each one of them by the load will make them dimensionless. So we're talking about dimensionless quantities here that take care of the energy falling into the solar collector and the load or the energy loss from the solar collector. So these values are given here, the X and Y. So we have FR prime. It's a modified parameter. Before we were exposed to the value of FR. Now it's a modified parameter. UL is an overall heat transfer coefficient. AC, area of the collector. Delta T, we're talking about the time frame. And then a reference, a certain reference temperature. Typically, they use the value of 100 degrees centigrade minus the average air temperature. This is all divided by L. L is the load. The load means what? Means I'm talking about a house that has a family of 4 persons. Each one of them is having or requiring 100 liters per day. So we're talking about 400 liters per day. Then how much would be the liters per month? And these liters need to be heated from which temperature to what temperature? So m dot Cp delta T basically represents our load here. The Y is basically, again, the FR value into tau alpha. Tau is the transmissivity, average transmissivity over the month. Alpha is the average absorptivity over the month. AC is the area of the collector, and HT is the incident solar radiation on the system. So one of them has to do with energy falling into the collector, and one of them has to do with the energy lost from the collector. Yeah, FR is the heat loss coefficient, if you remember. So both FR and FR tau alpha with efficiency data are provided by the manufacturers. We mentioned that earlier. This is a part of the manufacturer's specifications that are given. Then a modification of FR, which is FR dash, is a modified one based on the heat exchanger characteristics, which is connected to the storage. If we have a heat exchanger separated from the storage, but link it to it through pipings, for example, then we use this expression for correction. If the heat exchanger is located within the thermal storage, then we use this kind of correction. So the value of the FR prime here, it depends on how the storage is being connected to your system. Is it separated from the system, but just link it to it through a pipe, which like you have a solar collector with some sort of a manifold for the flow in and out, but the storage is away. Or you have a collector with a storage with it, like the ones that we have seen. You have a tank on the top of the collector where the heat exchanges go in there. And effectiveness here becomes the effectiveness of this heat exchange. The factor phi that we have here is the modification factor taking care of this quantity here and this quantity there. So this phi basically has a default value of 0.95. You would use this 0.95 if you do not have a value specified by the manufacturer. Say the manufacturer did not specify how much is the correction value, then you can take a default of 0.95. On the other hand, tau into alpha, again, tau is the transmissivity of the glass, alpha is the absorptivity of the the plate, the absorber plate, they should be corrected. Why corrected? Because the solar energy is not falling normally on the surface of the collector all the time. Actually, if you don't have tracking, then there's a change in the angle, and accordingly, these values are not going to be kept constant, and that's why we average them. Averaging them, a value of 0.93 is accepted as a conversion between the average and the given values. So 93% of the tau alpha has been accepted. Some extensive computer simulations was done by Transys. Transys is a very famous software that talks about transient system simulation. It is normally used for research. It's very detailed kind of thing that will give you analysis like on small time fractions. It provides values for f over a certain range of y and x. So the y range is about 0 to 3, and the x range is somewhere between 0 to 18, which cover most of the applications, by the way. For liquids, the first equation written red for f is being given here, and for air, the second equation is there. And you can see here, the difference between the coefficients is, between the two equations is basically the coefficients, the constants that are being used here. High flow rate of the fluid makes the collector efficient. High flow rate means that you are talking about turbulent flow, so it results in higher heat transfer coefficient. So there is pretty efficient transfer of energy from the hot absorber plate to the fluid which is passing inside the tubes. However, there is a limit, and the limit has been specified to be 0.015 liter per second per meter square for the water systems, and it is length 10 liters per second for every square meter in an air-based heaters or systems. If the flow rate is more than that, then it becomes, I mean, you are not getting much benefit there. There is a significant variation in the optimal storage size as well. It's not standard. 50 to 100 liters for water, 0.25 cubic meter of pebbles in an air-heated system per unit area of the collector. Actually, in many of these softwares, I remember one of the famous softwares, which is called Red Screen. It uses a typical value of 75. So it assumes that depending on the area that we have or the storage that you have for a system, 75 liters per unit of the collector area is good as a storage or recommended storage there. However, this value of 75, you have the freedom to change it, and the range can be seen here from 50 to 100. We have a figure here that shows a comparison between different F value equations for low and high value of F, for air as for water as well, where typical values have been used to produce this value. Liquid and air collectors do not have the same parameters. They are different because the fluids are quite different. The design of the collector is quite different, so that we don't expect them to have the same behavior. The graph is not used here to compare capacities of two fluids. It's just given here so that you can see how the behavior of Y and X are there. And normally, typically, when you have a figure like that, what you do, if you know what is the value of X in your system, you calculated it, you know the value of Y from the equations that we have given below. So for the figure that you have, you can get the corresponding value of F. Equations that we have here, it's been simplified. This equation that I've shown a while ago, that makes it much easier to calculate the value of F once you know Y and X. What is Y and X? They are basically some sort of expressions that are dependent on the collector, the load, and the conditions of the solar irradiation falling in. If you have this information, then you can simply do it by a calculator or using something like Excel to do the calculations for you. We were here talking about that. You can do that using in equations in systems like spreadsheets can be good enough for doing this kind of detailed type of calculations. some simulations have been done already, and corresponding values of profiles where constant value of f is being there and constant for different x and y values. Now let me clarify something here. F here is a representation of how much of the energy needed for your application to be obtained from the solar energy. So talking about F is equal to 0.2, 0.4, 0.8, 0.9, all of this is something you as a user can decide based on your budget. For example, I have a load from this building which is equivalent to this amount of gigajoules. How much of this amount you need to give by solar energy, and how much you still need to rely on electricity or maybe fuel to do it? Can you do it 100%? Yes, you can say if F is 1. So I'm going to make all my load based on solar energy. But this means that you are going to need more collectors. So the initial cost is going to be high. You are going to need more land to put, or more surfaces to put your collectors. If you have a place on the roof, then you are lucky. If you don't, then probably some people have to buy a piece of land to put the collectors in. This is all adding to the capital cost. So what is going to be the payback period? How many years would it pass before you get your investment returned? This is an issue. And the issue here becomes more significant depending on the type of fuel that you are using. If you are using electricity, electricity is rather expensive, which means that you can have a system that will give you an F value of 60 or 70%, maybe 80%, and you can make a payback period, or the quantity of investment you did for the capital cost can be paid back in maybe a couple of years, 3 years, 4 years. But if you are going to talk about water heating system that is utilizing boilers that are run by diesel, diesel is cheap. And in this case, you can find that using the solar collectors to reach for an F equal to 0.7 or 0.8 may have a payback period of about 20 years or so. This is significant. And I remember in the study that we did, one of the recommendations that we did, we said, we have one of two things to do. Either to increase the price of diesel so that you force people to move away from using boilers to using solar collectors, or do some sort of a subsidy of the solar collectors so that the government will interfere, maybe share the price with the consumers to make the systems being sold at lower prices. Having the issue of incentives is common throughout the world. In the United States, they reduce the taxes if you are going to put solar collectors on the top of your house. So part of the taxes, which is a very good incentive, instead of paying a certain amount of the taxes, you are paying like 60% or 50% of the taxes. And that's a good incentive for the utilization of solar energy. In Turkey, if you decided to move to solar energy, the government buys the collectors and install them on the top of your house. Why they are doing that? Because if they don't, they have to build a power plant, and building a power plant is costly. Maybe it would be better to have solar collectors spread in many places through the country, and this is going to decrease the requirement on electricity for heating or in fuel, because fuel is going to result in greenhouse gases, which is going to produce tons of carbon dioxide every year. And a part of the feasibility that we may do for utilization of the solar collector for water heating is there is some sort of a technical benefit. There's some sort of environmental benefit by reducing the carbon dioxide emissions. The carbon dioxide emissions is not only related to the utilization of diesel boiler in your facility. Say the facility is a hotel, you would not do it in a home. You're not going to put a boiler in your home for water heating, but use electricity. But even using electricity, it means that electric power is connected to a power plant somewhere. And this power plant is burning diesel or heavy oil to boil the water. And this is resulting in tremendous quantities of carbon dioxide being emitted there. So there is a formula that will enable us to estimate how much is the saving in carbon dioxide which is being going to the environment. So it's the benefit here is not only technical benefit, but there is some sort of a monetary value. I mean, you can do a spending a certain amount of collectors of money to buy collectors and install them now. But after a few years, when you paid back all this quantity, you are paying only a small fraction of the electric bill that you have, and the rest is being taken care of by the solar energy. And that makes sense when you are talking about feasibility of using solar radiation. So there's economic end, and there's also some sort of environmental benefit of reducing the carbon footprint. So the figure that we see in front of us here is for collectors that are using liquids, and the other ones for using air. Yes.
Yeah, I just wanted to ask, does it have some operational maintenance cost?
It is normally added. It depends on the economic model that you have, but in economic models, you have these values are defined as some sort of a fraction. For example, if the total cost is X, then the operation and maintenance is 10% X, the installation is like 25% X, and so on. So this is calculated into the formula of the economics of your system so that you can estimate the payback period.
But usually those collectors, what kind of maintenance usually you have to do? Replacing maybe the modules or?
You do not replace the modules normally. The modules are long living. I mean, the standard lifetime for this collector is somewhere between 20 to 25 years. You may need to do cleaning every now and then, especially if you are in places where there's a lot of dust storms and so cleaning is going to be needed. And you may replace the pumps maybe every 5 years or so. If you are talking about liquid water pumps, that might be needed to be replaced from time to time. But normally when you are buying collectors, say that you are buying, this is what we did. We bought evacuated tube collectors from a manufacturer. The representative here was in Jeddah, and we bought a couple of collectors, and they gave us something like 10 additional tubes in case some of the evacuated tubes are broken, so that we can replace them. So it's less likely for something like that to happen. Definitely it should happen. If you have a strong wind storm and the tree has fallen into your collectors, then you can expect some of them to be broken. So then you have to replace them. But this is some sort of an accident. But otherwise, these units live for long. I have solar collectors that I bought in 2009, and they are operating very nicely for water heating the beach. So they are basically designed to live for quite a bit of time. I hope I did answer your question.
Yes, thank you, Doctor.
Doctor, I have other question here.
Go ahead, please.
Maybe it's related to more economics way, okay? So here, how we can convince the customer or the regular user, okay, to use this system, okay, rather than the water heater that we have it, okay, in our houses or these things? Because even though if we're going to compare the lifetime of the water heater for, let's take an example for the water heater that's available in house, the American brand, it might stay for 10 years, 12 years, some of them 13 years, okay? So how we can convince the consumer, okay, to use such a system rather than that one?
Electricity bill.
The electricity, you're right, yes.
Yes, I mean that's the main thing. That I mean, you are going to say that you are going to pay 1,000 riyals only for water heating every month. So why don't you pay like 5,000 riyals now and buy a collector, put it on top of your house, and then you will save this. Maybe that becomes like in 5 months you are going to get your amount paid back, or maybe 7-8 months, whatever. But after that you are going to realize saving. And if you want to be more convincing, then it has to be some sort of a motion which is supported by the government, that the price of the collector is 5,000, but we are going to sell it for you for only 3,000. Then that becomes more tempting. And this is the kind of incentives. You can say that we are going to reduce the taxes, although the taxes here are not really connected to to your salary. It's taxes on buying and selling. But for those countries where they are paying annual taxes, reducing the taxes is the major incentive for people to do this. Actually, it's the incentive for people to do many things. Whenever the governments want people to go for a certain direction, they encourage them by having this reduction in taxes.
You're right. Yeah, you're right.
So
I
that's
think this
the
is
kind of incentives that are there. Maybe the issue of, and I just look at it as like a long-term vision. Suppose now that we are going to build a factory in the kingdom to produce these solar collectors. Then the prices are supposed to be cheaper. By the way, we have some of the finest quality of sand all over the world exists here in the kingdom. So we can get high quality glass by having the sands, but so far it's not fully utilized. If you are able to do that, to bring your own solar collectors, then you can have it at a moderate price, and the more that you are going to produce and sell, the less that the price will get. Accordingly, we'll look, for example, on the international level, the PV panels have been reduced by something like 70% in price over the last decade, from 2010 to 2020. Because it is spreading more, people are getting into it. And what encourages that more is that governments in some places have said that people, why don't you install the PV panels in your houses, generate electricity, add this electricity to the grid, and then take your electricity from the grid and you pay only the difference, so that you can find yourself sometimes, if you traveled for a vacation for 1 month and you come back, you'll find that you have something in your credit, which is given you, either you can get it as money or you can get it as consumption. So the point here is the incentives that can drive people into this direction. When this is there, more people are going to buy, which means that the prices are going to go down because of the mass production, and then everyone is winning.
yes, you're right. I think this is the
It
only
needs some
direction.
sort of a vision and plans to put this into the ground.
Yeah.
Fortunately, the vision of 2030 is putting some sort of a focus on the utilization of solar energy. And now you can find everywhere people are talking about solar energy utilization, be it solar energy coming from a PV system or a thermal system. On the thermal side, we are lucky because we are within the areas that is receiving substantial amount of thermal radiation, which means that a lot of things can be done here, and they can be done utilizing solar energy as a source of energy.
Yes, you're right. Yeah, very clear, Doctor. Yeah.
Yeah, we have an example. We can say it's a case study that we are going to get into, but I'd rather just to stop for about 3 to 4 minutes, and then we can resume again starting at this case study, and there is another one that's going to follow them. So it's just a short break, and then we'll be back in something like less than 5 minutes, inshallah. Assalamu alaikum. Back again to the case study that we have. It's about the utilization of the F-chart method for calculating thermal energy that we can collect from, you can see it here, south-facing liquid-based solar collector, which is tilted at an angle of 45 from the horizontal in March, with a climate variable having the following values. Air temperature is 6 degrees centigrade. Energy falling is 12 megajoule per meter square. Parameter KT that we have covered in chapter 9 is 0.62. Ground reflectivity is 0.2. at an altitude L of 38 north. A heat exchanger solar collector parameters have the following specifications. The heat exchanger effectiveness is 0.7. Cp of the heat transfer fluid is 3500 joules per kilogram Kelvin. Transport fluid flow rate, G, is 0.014 gram per second for every meter square. The coefficients FRUL, 3.5 watt per meter square Kelvin, and FR tau alpha is 0.88. Collector area is 10 meters square, and the monthly heating load for domestic water heating is calculated to be 2,500 megajoule in a day, which is in March 16, N is equal to 75, or March 15 in a leap year. If a leap year is the year where the February comes as like 29, then we can represent the month on the average. We are talking about March in general. So the analysis here is being done over a month. The first part of the calculations is to estimate the average daily insolation on the tilted solar collector. How much energy is falling into the collector. This is what we have been doing basically in chapter 9 of the book, which is talking about the angles and how to deal with the angles and so on. N, which is the number of the day, is 75. So the solar declination angle, which is delta, is given by that expression here. N is 75, so the angle is minus 2.4. The diffuse to global radiation insolation for K is equal to 0.62. The equation is equation 22 in your book in chapter 9. So HD over H, which is diffuse to total insolation, and KT is being given in the problem. So the ratio is 0.2759. The sunrise angle is being given here according to this relation as 88 degrees. So the value of RB, the ratio, is being given here according to this long equation as 1.33. And this equation also is there in chapter 9. If you recall the last example we solved in chapter 9, it has these parameters in. We followed them step by step. And then the ratio of the average total insolation on a tilted surface to the corresponding one on a horizontal surface. This is why we did all of these steps to reach for this R bar. And the R bar here is 1.2. So the total energy falling into our collectors is, or the average value is 14.8 megajoule per meter square. So this is the energy falling into the collector. We got this energy from the information of the energy and the location, energy falling into this city and the location. And to do that, we followed the steps that we have done in chapter 9 to produce this or to get these values. Now, having calculated the value of HT, the next is going to be going through that F chart steps that we have taken earlier. So the FRUL, which is the loss coefficient, is being given here, and the effectiveness of the heat exchanger has been given as 0.7, as you can see it here. So the value of FRUL is being calculated. The FR tau alpha taken into the averaging, or the averaging for the tau alpha is taken into consideration, and the FR tau alpha value has been calculated as 0.79. You substitute these two values into the expression of X and Y, then you can get the values of X and Y given here. Remember that the 31 number which is being used here is basically to represent that March is 31 days. The 3.4 is basically the FRUL, loss coefficient or loss coefficient factor here, and which is 3.4. And then AC, area of the collectors, has been specified to be 10 meters square. Delta T is the time. So if you are talking about a flow rate in kilograms per second, so 3,600 seconds per hour, 24 hours a day. So you can get 86400 seconds in a day multiplied by the number of days. So this is the delta T for the whole month of March. And then 100 is the standard or reference temperature minus T air, which is given as 6 degrees centigrade, average air temperature. This is multiplied by the load. They said the load is 2,500 megajoule. So the value of X is calculated accordingly. The value of Y, the same thing. If R tau alpha has been calculated to be 0.79, area of the collector is 10. And then the HT value that we have calculated in the previous slide, which is 14.8 megajoule per meter square, has been given here. And 31, again, this is the number of days in the month. And L is the load. Substituting X and Y, you can get a value of F, which is equal to 0.84. So the average thermal energy, which will be handled by the collectors, is 0.84 of the total incident energy on the collectors, and that represents 2,500. So 84% of your load is to be carried out by the solar energy. So your solar fraction is high here, which is 84%. Now, we did this analysis for the month of March. What needs to be done is to repeat this for the rest of the year. We have taken the middle of March, 15th of March, as a representative, the day number 75. So what you are going to do, you are going to repeat this for every month. Take 15th of every month and do it for January, February, April until December. Then you are going to collect the whole information here over the whole year. And this is basically what you are looking for. So it's going to be repeated for every month. Assign monetary value for the energy. This would be the natural next step. Compare the benefit, the annual benefit, to the cost of solar collectors, and then this will bring this kind of level of solution that we have from the collector side to the system side, to the system design. What we are doing here, we are saying that for March, the collectors are taking care of 84% of the load. But what if we need to upgrade a little bit and look at the whole system? To do that, we can look here at the F chart for the system analysis.
Doctor, if you don't mind,
Go ahead, please.
X and Y represent what?
X and Y represent dimensionless parameters that are used in the estimation of F formula. Remember that the equation that we are having for F is a function of Y and X, capital Y and capital X, which are dimensionless parameters that take care of the energy falling and the energy which is falling into the solar collector and the energy which is being escaping from the solar collector. The difference between them is the useful energy that you have. And it has been coming up by computer simulations that using this value is going to make the way shorter for us instead of going into very much detailed analysis. So you just do it by calculating these parameters of X, and which is this. It's talking about the energy losses from the collector that you have and the energy falling into the collector.
Here, Doctor.
You are putting it here in a dimensionless form so that you can easily estimate the value of F with simple calculations. You don't have to go through detailed calculations then.
Yeah, sure. Thank you very much.
Doctor,
Yes.
in the second grid equation for air, is there a
Yes.
plus at the end of the equation?
Let me get, actually, yes, for the water, it ends with a minus, but for the air, it ends with a plus. Let me get into the equation. In which slide was it? I think it was later. Yeah, X and Y. And then coming to the value, yes. So yes, it should be a plus here. Sorry, it's missed. Or it's maybe a minus, because I remember that there was a difference between them. So that's something I need to correct before proceeding. I will correct it in the original file that I have. But anyway, there's some typos that I took care of. Some of them after creating this presentation, but some of them were just left to be still done. So now I'm into my system trying to browse through to reach for this equation, and fix this expression of F for the air heating system. I know that this is there in the book, and just to make sure I fix it now while we are in this part. Yes, the last one is a minus, it's not a plus. So I'm getting into the expression and I'm in the yes, actually I just even found another type here, extensive computer, and then when it comes to this equation, then the last thing should be minus 0.0095. And I'm saving it so that we can make sure that it's so this has been, oh, it's been even corrected here, minus 0.0095. Thank you for bringing this up.
Yeah, thank you, Doctor.
Now, when you are talking about the system design, going back again to the continuation of the example that we started in here, that what we are looking for the best size of solar collectors to meet the expectations. And this would vary, another typo that we have here, due to the climate changes, heat needs, cost of the system, and the component characteristics. So there are some parameters that come into the picture here that needs to be considered. Not only it's related to the loads, but the conditions, the weather conditions that that we are going through is another important parameter. The F-chart method is then expanded to account for these changes, and an example of water heating is being demonstrated. So this is the case study. It's talking about a design of an optimally sized solar collector system in Sacramento, in California. We need to estimate how much useful energy the system provides in an average year, its monetary value. The solar heating system should provide domestic water heating only, so it's not concerned with the space heating, only for getting water in. You are considering a solar collector with rating data as follows: the FRUL, again, so excuse me for another typo here, that the R has got to be a subscript. Where did it go? Yes. Oh, sorry. Is 4.57 and the FR tau alpha is 0.737. The collector is tilted 5 to be the latitude +5, which is often used for the overall year performance. And if you recall that, I told you maybe once before that when you are building, say, a solar cell or putting a solar collector in Dhahran, then we look at the altitude of Al Dhahran, and then we just, or the latitude of Dhahran, and we just consider that as our angle, which is there for best practice. Now this is given it more meticulous to be the latitude +5. 43 from the horizontal is the tilt angle for this place. The area of the individual collector is 2 meters square, which means that every collector is 2 meters square in net area. The expected effectiveness of the heat exchanger is 0.75 for a flow rate of 0.014 kilogram per second for meter square, and CP for 3,500 joules per kilogram Kelvin represents the heat transfer fluid as it passes in. Storage is taken to be 50 liters per meter square based on the collector area. So this is on the low end of the suggestion of the storage, 70 to 100. And I remember a while ago, I just mentioned that softwares like Red Screen take a default value of 75, which is then in the middle of the range of the storage. Every solar collector has a price of $750, and there is a flat price of $2,500 for installing the pumps, the pipings, the controls, and this kind of accessories, and $2 per liter of thermal storage. So we're going to see how much is the storage that you have, and then the price of the storage is expected to be this way, with the heat exchanger included. Conventional water heating by electricity is going to cost like 16 cents per kilowatt hour. So we need to design for a family of 4 persons with 1 additional adult who live in the home from June through September, make a reasonable assumption of daily water use of household. Water specific heat is 4180 joule per kilogram Kelvin. The home is located as a latitude of 38.5 north. Meteorological data for Sacramento is given in a table here, and snow is not normally occurring in Sacramento. It seldom freezes, and the ground reflectivity of 0.2 is expected for all months. So this is some sort of the requirements and the weather conditions of the area that need to be considered while you are supposed to be designing a heating system for a family of 4 persons. The table that we see here has the weather data of that city, Sacramento, and the K parameter, which takes care of the ratio between the diffuse and the global radiation. Assume the installation cost will be amortized at a yearly cost of 12% of the installed cost. So we're going to take like a simplified economic model. We're not going to get into very much details of that, and assume taxes, credits, deductions, and all of them are factored within this value of the 12%. These are the weather conditions given month by month, January, February, up to December. And then the monthly heating load has been calculated here from January to the end. The way to calculate the heating load actually is, the assumption is everyone uses 100 liters of hot water daily, which is to be heated from 15 to 25 to 55. Actually, they have not specified the value 25, but the way it came from here is 60 degrees centigrade is what they call the pain threshold for a human. They cannot withstand more than 60 degrees centigrade. It will be painful. And that's why, and 50 is somewhere is average values of minimum heating. So that's why they took like a compromise of a temperature of 55 degrees as the required needed for the degree needed for the hot water temperature. Accordingly, the load can be calculated here. We have 1 liter, I'm talking about 1 person now, M, CP 4180, and the delta T 55 minus 15. So this is going to provide us with a value of 16.7 into 10 to the power of 6 joules. Now I have to tell you that there are a couple of ways to do the calculations. You can assume that the temperature is always 15 all over the months and calculate the values, and it will give you the values here in the table. Some other school would say, no, let me take the air temperature for every month and consider the water temperature is equal to that value, and accordingly it is going to change over the values that we have here in the table. So both of them can be done. You are designing anyway, and in your design you have the freedom to do assumptions as you are moving in. And at the end, having these values of T water in as 15 constant all the year, or changing according to the values that you have here, it is 7 in January, 10 in February, 12 in March, 14.6 in April, 18.5 in May. And you know, sometimes it's less, sometimes it's more, so it may balance each other. But anyway, what he's doing here is that he's fixing this value as 15 for all months. Assuming that there is some sort of 25% losses, this is a little bit on the high side, but this is the assumption given here anyway, as if 25% losses in the storage and piping then a person was going to need this quantity of joules per day, 22.3 into 10 power of 6 joules per day. Then this needs to be done per month, and the number of persons would be there. So the cost, I mean, of the monthly heating load is being given. Actually, I did an Excel sheet that I might be able to upload to the Blackboard, or you can create your own one as well. Each kilowatt hour of purchased electricity is going to cost 0.16 and provide 0.65 megajoule. Where this value comes from, I'm talking about a kilowatt hour. And the price for kilowatt hour is 0.16. Then what will be the price of megajoule? A kilowatt hour basically is kilowatt into 3,600 seconds. And this is where the 3.6 comes from. Assume that all the power given by electricity is be converted into heat. So we are talking about electric coil, which will convert all electric energy into heat. So it's 100% efficiency. Then every gigajoule of heat is going to cost $44.4. How did we calculate that? I put it here in this blue line here, that each 3.6 megajoule is going to cost 0.16. So what will 1 gigajoule is going to cost? And then you can relate it to this value. If we know the collector area, we can know what is the F value that we are going to obtain. So how much of the total energy is going to be taken by the solar. There's no closed form solution for this, and we cannot make a recommendation. We cannot say that use this number of collectors so that you can get this area. Neither than the software will do that. It will give you a recommended value. And to complete the analysis, you better change the number of collectors and see how much is the effect in terms of saving in energy and in terms of cost as well. For example, if you are using a program like RedScreen, you can put the information of this example there. It will tell you, we recommend that you use 6 collectors. But as a designer, you should say, what if I used 4? What if I used 8? What if I used 10? And then you can come up with an optimum condition there. And that's why in the example, it asks for some sort of an optimization there. So what we are going to do, like the previous example, we are going to follow the analysis that we did in chapter 9 to estimate the energy falling into the collector with a tilted angle of 43. I'm not going to repeat it because we did in the previous example. And this is going to give us this quantity. So the quantity of energy falling into the collector in every month is being given here. The values of X and Y are going to depend on the collector area. So we are going to calculate X and Y, and they are going to be again tabulated in a table. Remember that we are doing it for every month alone. In the previous example, we did it for March. Here, based on the data given, you are going to do it in every one of the months of the year. And the values have been given here, X over A, for the values of the months from January to December have been given here, X over A and Y over A. You are going to use X over A and Y over A here to get the value of F for January, and then F for February, and then F for March, for April, and so on. So you are going to end up with 12 values of F. Then if we consider an array of 4 collectors, this is now we're going to work with an assumption of 4 collectors. So the area of 8 meters square, the value of X and Y are given here in this value, in this collector. So the yearly average supply of the collector is the summation of the gigajoules. You are going to assume all the quantities of the gigajoules that you have in this table. And you are going to see how much is the price for all of it, which will result in a price of electricity of 1,050, which means that if you are going to have this load and you are going to use an electric domestic water heater, then this is the bill that you are going to pay, $1,050. Now, having the values of the X, Y, and calculating the F F here represents how much of the energy is going to be considered or taken by the solar collector, and how much energy that you have saved every month. And the savings here are given by this, which means that the remainder of the 40% is this. This is 40% of the quantity that has been given in this table. For example, let's talk about January. January requires this gigajoules per meter square per day. The solar collector is going to cover 40% of this. So the remainder with the 60% is basically what's been given here as gigajoules. And this has been specified for every one of the months here. Now, the calculations that have been given here are based on 8 meter square collector area. What if we have different collector areas? For example, 2 meters square means 1 collector. To 16 meters square, it means 8 collectors. Here we said that we have 4. So to do that, the whole thing is being repeated for different values of collectors. So the analysis is being done for 2 collectors, 3 collectors, 4, 5, 6, 7, 8 collectors. And for each one of them, you are producing the yearly consumption or the amount of energy which will be taken by the collector, and how much is the yearly saving value. And when you put that in a figure, you'll find that the values here are, this is the yearly value of the monetary value corresponding to the utilization of the collectors there. But when you get to the savings are being specified here. You have, these are the areas, and this is the price of the collectors. Remember, a single collector is going to cost $750. So 4 collectors, 4 meters square, 2 collectors is 1500. 16 meters square, 8 collectors means 8 by 750, it will give us this value. So this is the price of the collectors. This is the price of the storage. Remember the storage, they said that we are going to have $2 per liter, and we're assuming 50 liters per meter square. The meters square are here, multiply 4 by 50 by 2, then you are going to get these values as price for the storage. And there is a flat price for the installation and the pipings and the controls. So this is the total. And this is the share of yearly value, which is the 12% of the total. And that would be the net value. The net is what is being plotted here to show what's the optimum saving, which means that going for 12 meters square, which is 6 collectors, is going to provide us the best saving for our system. You see here, when we are talking about, when you look at the steps that are being followed for analyzing this problem, you can find the steps are many, but it is some sort of a standard sort of steps. If you are doing it, for example, if you establish it in a program like Excel, you are going to do it once and just change the areas, and everything's going to be changed accordingly. So it's once you set it up for the first time, the rest is going to be just simple to do. Now, there are some thoughts that are based on the calculations that we did in this example. It is based on weather conditions. Remember, when we started with the weather conditions of Sacramento. What if the weather changes from one year to the other? This is going to change, which means that the numbers that we have used here, suppose that you said you are going to use 6 collectors. For example, where's the best saving? Yeah, the best saving is coming from the highest value is here, which is basically 6 collectors. So the saving is $356. If the weather conditions then the next year have changing, you are going to have savings. It might not be 356, but it will be an ultimate saving anyway. So weather conditions are going to change, making this value change, but the change here, hopefully it will not be significant, because the way that they are measuring the weather conditions, it's an averaging over a large number of years. For example, I recall when they started to create the Saudi Atlas for the weather conditions, they have collected monthly and weekly conditions of the weather for about 20 years at least, which means that whenever you have longer period of time, then you have more confidence into the average value that you have. But anyway, it may change from one year to the other.
Doctor,
Conservation would reduce the consumption. Why should everyone use 100 liters per day? It can, if it can be reduced, then you are talking about less consumption and accordingly less bill that you have to pay. Maybe if your consumption is less, then the solar fraction is going to be higher and you are going to pay less because solar energy is going to take more and more load of your needs. Cost of the collectors may change. Hopefully it would reduce. This is what's happening with solar panels, that it has been reduced over the last decade. And I would assume that the solar collectors would reduce in price as well. If you have a local manufacturer, then they are going to reduce further. More detailed simulations might be needed if you need to reduce the assumptions. While we are operating here, we made some assumptions. One of them is assuming that the constant feed temperature of 15 degrees centigrade is going to be there all the time. What if we said, no, this is not going to be like that, but every month we expect to have its own different temperature? Then your solution is going to be a little bit more accurate, but it needs a little bit more time, or the solution, the calculations are going to be a little bit more. And the same thing applies for any one of them. The heat exchanger cost would increase monotonically with the size. The bigger the size, the bigger is the heat exchanger. And this increase is not linear. Sometimes a bigger size is going to cost many times more. Cost of electric power is not constant, it changes. Accordingly, if it increases, then you'd expect the bill is going to increase. Definitely, it will be increased for you as a user at a lower rate if you have solar collector compared to not having solar collectors. But again, that's something can get into the equation and change the numbers. More detailed economic analysis can be used. I mean, we have basically used a simple economic model analysis, but this can change definitely. And if you need to do air heating, you are going to follow the same procedure that we have done. It's only probably changing the F equation is going to be the major change that you're going to have here. Definitely talking about the MCP delta P, we are going to talk about how much will be the flow rate of the air. The CP value of the air is quite different from the water, and what is the temperature you're expecting from an air system. But that would basically be for space heating, not for just hot water cooling or heating like that. Now, talking about the issue of optimization of the solar arrays and the heat exchangers accordingly. Some sort of a trade-off might come here. If the heat exchanger price is too high, then what's best to do? Should I keep on the big size of the heat exchangers, or maybe move at the lower size of the storage and increase the number of collectors? What's going to control this is basically the price. How much is the price of the collectors? And how much is the price for the heat exchangers? This is going to be the determining factor. And you can see here talking about the match between the solar collector array with the storage and the heat exchanger for liquid heating. It's depending on the relative cost as I just mentioned. If the collectors are expensive compared to the storage, maybe going for a bigger storage is going to help. Vice versa applies. So a balance is obtained by estimating the base or doing an estimation based on the marginal cost of the collectors and the heat exchanger system. How this is done? If we assume that there is a factor C sub C, which is the marginal cost of adding collectors, and CUA is the marginal cost of adding storage. And the collectors, basically C collectors, number of collectors, which is going to be reflect directly in the total surface area. Whereas the heat exchanger, the improvement can be either increasing the size or increasing or improving the heat transfer coefficient. So it's the UA value, the conductance value as in general, which is coming with a price. So we are comparing the prices of adding more collectors versus the prices of adding more heat exchanger capacity or storage capacity. So we're going to follow a formula that has been proposed to estimate the optimum ratio between them, and it's given here. The UA value over AC is given by UA is the conductance, AC is the area of the collectors, and this is going to equal to the modified loss coefficient. UL is the overall heat transfer coefficient, price of the collectors, cost of the collectors here, or cost of adding the collectors, divided by the cost of adding a heat exchanger for the capacity. Compare this value and see. And based on that, you can make your judgment. So when you apply that to the previous example, each collector is worth $750. It's 2 meter square area. So C sub C is 375. And then we have given that the value of FRUL is 475. And with assumption of $600 for 1500 UA, that makes the price of UA is 0.4. Accordingly, the optimum value is going to cost us like UA over AC is 65 watt per Kelvin. If you have a collector of 12 meters squared, it will be optimized with 780 watt per Kelvin. So you are going to look at what is the optimum value and whether you change this or change that, are you going to go away from the optimum value or not? And then you would make sure that you are at the right estimate of the price in terms of number of solar collectors and size of the storage system that you have. I brought you one more example. Maybe or just something like less than half an hour away from the end of our class. But I brought another example that I thought it would be beneficial, going through some sort of hand calculations that are simpler to determine the value of the F factor. We have taken an example here of a city in California, which is Sacramento. And then I just found another work that has been done for a city in Nigeria for using solar energy for heating. And that was interesting. So I brought it to you so that you can have a look at it together. So I'm going to end this presentation. I'm going to bring the other one in so that we can look at this kind of estimation.
Doctor, I have a question here.
Go ahead, please.
Can we just specify some time to talk about the final exam?
We will.
Okay, thank you.
We will. I mean, the example that I have will not take us like 10 minutes, and then we can talk about the final exam, inshallah.
Sure, thank you very much.
I will just close this presentation and get the other one where I have this example. Come on, why it's not opening? Closing the dialog. Discard. Oh, yes, here we are. So, and I'll tell you why this presentation or this condition that I'm taking is different from the ones that or is separated from the ones that we had earlier. And which is basically because, let me bring my, yes, when I share. Oh, why it's not, I should be sharing the presentation right away. Yeah, so I hope it's fine with you to have this example given in Arabic. I would assume that all of you are speaking Arabic, so I hope it's fine then. Now, what we have basically is that example that we have. I'm just going through quickly the F-chart method again in terms of the calculations. What we need to do is to calculate the values of X and Y, and the values of X and Y as dimensionless parameters are given here. X is the losses, المفقودات, المجمع الشمسي اللي هو solar collector, which is divided by the load, which is L. Y is the energy which is absorbed by the collector, المجمع الشمسي. Again, it is normalized by dividing by the load. A is the area of the collector. And then again, FR is the heat removal coefficient that represents the effectiveness of your system. UL is the overall heat transfer coefficient, and TREF is a reference temperature, which is basically estimated as 100 degrees Celsius. Fahad, you have a question. I can see your hand. Go ahead, please.
No, sorry, that was from earlier. It was about the Atlas when you mentioned it.
Oh, yes.
It has not been working in the past couple of weeks. Do you know if there's a reason to it?
You are talking about the site of
Yes.
care?
Yeah.
It normally goes under maintenance every now and then. So maybe that's why.
Okay.
Maybe updates on the software or something.
Okay, thank you.
I've not been looking at it in recently, but I mean, from time to time that happens.
Okay.
TA is the average temperature of the surrounding air. L again is the thermal load. Tau alpha is the average of النفاذية, transmissivity. معامل الامتصاص, which is alpha, the absorptivity. HT is the average of radiation falling into the unit. N is the number of days. And F prime R over FR is a function of the efficiency of the collectors. It can be given by the equation here, which is specified as equation number 3. M dot flow rate معدل السريان, CP الحرارة النوعية, specific heat. And in case of no heat exchanger, this ratio is taken equal to 1. If you are talking about water, the CP is 4.2. If you are talking about glycol, ethylene glycol, then it is 3.85. It's a mixture between them. Then you can calculate the value of CP to be given based on that. مساحة السطح بالنسبة لمعدل السريان 140 متر مربع لكل كيلوغرام. According to an area of 2.97 square meter and a flow rate of 0.0214. This may vary from one collector to the other, and this is given normally based on the collector type that you have. There is again a correction for the storage. If in some softwares or some programs, they taken the storage to be 75 liters per every meter square. And sometimes, as you see in the previous example, you have taken it as 50. So that's something, again, as a designer, it's all up to you. If you are going to take it less or different from 75, then this is a correction factor that you have. Standard is the 75, actual is the actual area that you have. And accordingly, this is the F equation, which is used for air. For water heating, and at the end to calculate what we call the solar fraction. The annual solar fraction represents how much of the total load that you have is going to be taken care of by the solar collector, so that the remainder will be taken care of either by electricity or by a boiler with diesel fuel or whatever it is. So we have an example here. عايزين نعمل a system for water heating لعائلة تتكون من 6 أشخاص, 6 persons in Nsoka, in southeast of Nigeria. This basically was given in a paper, by the way, that was published. I took it and I just redid the work to make sure it's clear here as an example. Using solar collectors, glazed solar collectors, the angle beta is 22 degrees with the horizontal, and it has the following characteristics. These characteristics are the characteristics of the solar collector, which comes from the manufacturer. If RUL is 4 watt per meter square, if R tau alpha is 0.74, tau alpha over tau alpha normalized is 0.94. Remember, in the previous example, we said 0.93, so it's not too far. The tank is 120 liter per meter square of the area. The heat transfer FR coefficient is taken as 0.97. And there is a table that gives the H value, HT value, متوسط الإشعاع اليومي. If this value, remember in our previous example, we have calculated this value based on how much is the total radiation falling into this area. And then based on the tilting angle, we came up with this value of HT diffuser over the total HT. And then we can get how much is the actual amount of energy falling into the collector. Here in this example, the value of HT is the actual given on the collector right away. So it has saved the kind of calculations that we did that's related to the angles and so on. المتوسط اليومي للإشعاع في يناير 16.6 ميجا جول لكل متر مربع. And what we need to do here is to calculate the value of F, the F or the solar fraction that this unit can provide for solar collectors that are occupying 20 meters square using the equations that we had earlier. الحمل الحراري هنا بالنسبة لكل شخص is being calculated. We are taking January 31 days as an example. So M, mass flow rate of the water that needs to be heated, CP, T water minus Tm. So this is inlet minus, like water exit minus inlet temperature for heating. Assuming the temperature is 26.6 Celsius, and we need to heat the water to 80 degrees centigrade. Now, this is an interesting thing to look at because the threshold of pain is 60 degrees centigrade. But the point here, when you are using hot water, when you are taking a shower, you don't just open the heat water and get it right away, but you do a mix between some hot water and cold water. So maybe going for 80 degrees centigrade is going to make you use less storage by heating water at higher temperature. And then when you use it, you don't use the hot water as is, but you take less hot water and you mix it with cold water to get the temperature that you want. The quantity of water needed is 120 liters or 120 kilogram. So the load is being calculated as 0.83 gigajoules in January. For an area of 20 meters square, the values that are calculated for X over A and Y over A are given here. And the correction of the XC for the tank is about 0.88. Then this value is being considered for the corrections of the solar energy that is needed in January. And at the end, what we did is the kind of correcting value multiplied by, or the F value that we have, multiplied by the load on this month, and then you can get how much energy given by the solar energy for this month. This is going to be extended for the several months, and let me show you the table here which is doing that. So basically you have, this is how many megajoules per meter square which are incident. This is the external air temperature, and this is what I told you. In the previous example, we have taken a value of 15 as constant. Here we are going to say that this value is not constant because it changes from one month to the other. So we are taking the average monthly temperature. And this is needed for the load calculation L, because L here is M dot into Cp into 80 minus this temperature, assuming that the water temperature coming to the collector is equal to the air temperature. Then we are calculating the factors X over A, Y over A. We are correcting these factors for storage. And then at the end, we are calculating, substituting in the F equation and getting the value of F. This factor multiplied by L is being given here. And what we need to do, we have done that for every one of the 12 months that we did. At the end, we are collecting what is the total load over the year and how much is the value of FL over the year. And then going back to this equation, that the F factor is being calculated as this ratio, like how much of the total energy needed is being given by the solar collectors. And it shows that for this system, we have a solar fraction of 44%. I'll get you back to the equation that I was referring to, that at the end, we are looking for this. The solar fraction is sigma FI-LI divided by sigma Li, which is basically how much is the load that we need. So how much we can afford solar energy to get part of the load, and this has been done all over the year. This issue of table shown here is what would you do typically in a system like that. So that over the year, you see your requirements, and at the end, the difference or the ratios between this is basically what you can afford through the solar collectors. And this is your total needs. So this ratio provides that how much is the total need is attained through solar collectors. So I hope you'll find that simple. I'll put the paper where I got these calculations from. I think it's some sort of a paper that I'm not sure was it how many years old, but again, that's another example of utilization of the solar fraction or the F-chart method for the estimation. There are different softwares that are there. Maybe some of you, I just discussed it with them. And one of the softwares which is available is called RedScreen. You can make use of this software to do the required calculations of the solar fraction. And it even gives you more detailed calculation related to the technical feasibility, the environmental feasibility, how much carbon dioxide you are saving by using this solar energies in, and how much would be the payback period of using the solar collectors, provided that you know what is the price of the solar collector. The program has a built-in software that has hundreds of companies that are producing solar collectors with detailed specifications of each and every collector out of these. The latest version is updated. I worked extensively of version 3 of the RedScreen program, but I had a problem then because some of the collectors I selected were outdated, that are not produced by the companies again. So I had to contact one of the companies and get the latest specifications of the latest collectors. But version 4 has an update. So I would assume that the collectors that you have are going to have updated information in. So if you are interested, the software has two versions, RedScreen and RedScreen Professional. The professional one is definitely you have to pay for it, but the other one is free if you need to test your, or maybe you need to exercise, like say sitting down and having some time and say, what if I need to have solar collectors for my house? The climatic data of almost all major cities in the world are given in that. It has so many cities within the kingdom. So easily you can get the climatic data of your city that you are staying in. You can, based on the standards of 100 liters per person, you can estimate how much water will be needed for your family needs. And then you can do sizing for a solar collector in your own house. That's why I said in the beginning, I hope that you can find this this class today interesting, because that's something that you can apply not only for the course, but you can at your leisure time, you can just come up with an estimate of the solar needs for your own house. The software is not only about solar heating, but it has so many other applications related to solar energy. I'm not sure if wind energy is there or not, but solar, I know, I'm sure about it, that it has examples. It has built-in case studies that you can use and modify, and including PV utilization. So many things are there. Even for the issue of different renewable energy sources like the biomass, it has a version of the biomass where you can apply it. We don't need biomass in the kingdom because we don't have lots of wood. But maybe some of the biomass waste can be thought of as a sort of energy in specific places in the kingdom. So that's it for the coverage of our class today. And maybe in short, we can say something quick about the final exam. I've been in discussion with Dr. Mohamer lately, and what we agreed upon, it seems to be in line with what you have requested. So so far we have 3 class tests. The first one of them was in Rankine cycle. The second was on Brighton cycle and the combined cycles. The third one has the nuclear energy as a part of it. So the exam, the final exam, is going to be on the part after we covered the third test, which means that definitely chapter 9 has to be there because it's a part of what we have done today. We're talking about the angles or so, but it will be from the end of the nuclear part. Nuclear part is not included up to what we have covered today.
دكتور يعني كل اللي قبل النيوكلير وقبل مش معانا في الاختبار.
نعم مش معانا في الاختبار. Unless then I can include it then.
كيف يا دكتور؟
يعني لو انتم مصممين ان احنا ندخلهم fine.
لا احنا مش مصممين.
لا يا شيخ.
That's what I expected. Yeah, I was just joking. I know that. I know that.
بس دكتور ما قلت لنا ايش صار على الاسئله حقت المالتيبل تشويس اللي كان حاطها
Oh yes, actually what I'm going to do is that I'm going to take out this question from the marks of quiz number 3 or test number 3.
So all multiple choices.
It will be the two problems that were there in the papers that you had.
دكتور خلها بونص لو سمحت دكتور لانه
This is the bonus.
اخذت منه وقت يعني.
This is the bonus that these things are not there. They only took like 20 minutes of us, and then the rest actually did not need more than half an hour to solve. So I'm just taking it all out of the calculation of the grades for this test.
طب دكتور معلش
يعني 100% of the test will be on question 2 and 3 يا دكتور صحيح؟
Yes, exactly 2 and 3. That's right. Only those.
شكرا يا دكتور ما قصرت.
دكتور طيب انت عرفت ليش حط الاسئله هذه او من وين جاب الاسئله؟ يعني
Well, I did not meet him so far, but definitely what I can do is that I can provide you the solution for this multiple questions, at least for your knowledge that I mean out of the course you come up with like the BWR or the PWR or the thorium breeder. You would know, for example, each one of them is known to be best in what. So I make it available so that it's additional information that's useful, I hope, inshallah.
Doctor, can we have our marks on test 3?
Excuse me again?
Our grades on test 3. How much we got in that?
I will post it. I've not yet finished it so far, to be honest. So this week you should be able to see this kind of details, inshallah.
Okay.
طيب دكتور لو ممكن الاسبوع ذا اذا لو وقتك يسمح نعمل هيلب سيشن شويه على المواضيع اللي فاتت بتاعت السولار.
Yes, why not? The parts that I've covered, I mean, we can again like meet on Tuesday at 8.
Tuesday.
I can cover it, and if you want something from the concentrated solar or the wind, maybe you can just communicate with Dr. Mohamer to provide another one.
تمام.
It will be fine to do that.
دكتور راح يكون من عندك السولار.
Yes, I mean the parts that I've covered in the course, we are going to discuss it in that, and then whatever is related to CSP, concentrated solar, or the wind, that will be by Dr. Mohamer. Just arrange on a time with him, and then I think he will not mind at all. For us, it will be 8 o'clock on Tuesday, inshallah.
So, Doctor, our exam will be from renewable energy up to today lecture, isn't it?
From the end of the nuclear is not part of it, onward up to what we have finished today, inshallah.
Yeah, that's mean from renewable, yes.
Yes, that's right. Actually, many people look at the nuclear as renewable, so that's why I was just conservative about the word renewable. But from the end of nuclear onward is what we are going to be including.
Yeah, sure.
Excuse me?
Yeah, I'm just saying that we already had that test 3 on that.
On
the solar and radiation.
Yes, but the point is the examples that we have today, they have the issue of converting like the solar energy falling to reach for the amount of solar energy falling into the collector at its tilt angle. So this is an integrated part which we cannot take out. So that probably will be the overlap.
دكتور لو سمحت، هل ممكن الحصول على مجموعة أسئلة تغطي جميع الجوانب اللي ممكن نختبر فيها يعني جميع
I think if you have gone through
4 5 6 أسئلة دكتور.
Oh, we have the last part. There's no homework for it. Maybe I can release some problems. Hopefully I can find some problems that I can give today or maximum tomorrow, and then we can look at their ideas on Tuesday. So it will be some sort of a practice on this part. Sure.
Doctor, one question. We want to do a formula sheet for the final.
I will prepare that based on the problems that will be given. Whatever formula needed, it should be provided.
والله دكتور
here in the university, which means that it will not be an open book thing. So whatever is needed, I'll make it available in a formula sheet.
Doctor, can you allow us to have each student have one sheet with him?
The problem is that it will not be fair, because I mean when I provide the formula sheet, it will have the information that I'm sure it's needed for all of you. When you prepare it yourself, some will prepare it to be adequate, some less adequate, some more than adequate. So let's standardize it, and I will provide the formula sheet.
ما قصرت دكتور، شكرا.
Questions, Shabab? So it's settled now for the final exam. We know what we'll do. We're going to have like, I will provide a help session on Tuesday. You just agree with Dr. Makhemer on the time that you liked all together. And the exam is on the 26th of December, which will be a Saturday. It's 7 p.m. and it's in building 54, which is the building opposite to Riyadh Bank. And then it will be easy to find it.
فورمولا شيت ممكن يعني انا بقول لك ليش يعني احنا الواحد بده يسويها، لان الواحد يتذكر القوانين اللي هو حطها، لكن اذا كانت فورمولا شيت جديده ياخذ وقت لين يستوعبها.
I'll solve the problem for you. I'll prepare the formula sheet and I will post it in the Blackboard like a couple of days before the exam.
حلو كذا تمام.
خلاص تمام كده؟
تمام كذا الله يعافيك.
طيب خلاص اوكي.
على اساس لا يكون في سربرايز يعني بس.
لا there'll be no surprise inshallah. So you'll just have it and just be used to it, the way it looks like, the way it's arranged anyway.
مش جديد يا دكتور يعني يا دوب مخي شويه.
ما سمعتكش عفوا.
اقول احنا الواحد بيشتغل دماغه على الديزل، عشان كذا نحتاج وقت عشان نفهم الفورمولا شيت نذاكرها.
لا it's okay. You'll get that inshallah. Yeah, the sooner the better. I will do it as soon as I get the exam ready and release it to you inshallah.
Doctor.
تفضل.
It will be similar manner like test 1 and 2 and 3.
Yes, more or less.
It will be solving the problems only. Okay.
Yes, if there's something else other than that, then I will post it to you. But more or less it will be like that, inshallah.
Okay. The duration it will be 2 hours or?
Maximum 2 hours and a half.
Okay.
It will depend on the number of questions that we'll put, and also this information I'll try to make it available for you this week. So this week, expect from me to put the duration of the exam, the number of problems or number of questions that will be there, and the formula sheet, inshallah, before the end of this week.
That's great.
جزاك الله خير.
Okay, يا شباب. توفيق إن شاء الله بإذن الله.
الله يعطيك العافية. جزاك الله خير يا دكتور.
الله يحفظك. في أمان الله يا شباب. مع السلامة.
في أمان الله.